Good morning, everyone. So we have a full schedule today. So in the morning session and in the mid-morning session, Professor Snigdha Thakur from IISc Bhopal is going to give us some talks on active polymers. And then in the afternoon, we're planning to hold a discussion session just like we did yesterday. By the way, how many of you enjoyed the discussion session yesterday? Okay. How many of you did not? Maybe. Can be better? Okay. Anyway, so we're going to have the discussion session. Whatever question you have, Professor Snigdha Thakur is going to be there. We're going to be there. It can be a free-flowing discussion. You saw that how it went yesterday, right? So it will be something like that. And then in the afternoon, after tea, we have 2 research talks. And then after 6 o'clock, you're free to do whatever you want to do. So with that, I welcome Professor Snigdha Thakur. And yeah.
Thank you so much. And yeah. Good morning, everyone. First of all, I would like to thank organizers for giving me this opportunity to talk to all of you. So what I'm going to do in next few hours is just going to tell you about the work that we are doing in the lab in our group. And the way I have planned is, instead of going directly to what we do, first talk, maybe I'll try to tell you how we do things. Okay, so I'm a computational person and I do simulations, different types of simulations I've done throughout my career. But I will try to stick to one technique in this course, and we'll try to take you deep in that technique and tell you what all things people have furnished with those techniques, and what then maybe in the second talk, or maybe by the end of this talk itself, we'll start talking about what all things that you can do with this technique. Okay? Okay, feel free. I'm sure you all have been doing this, but again, feel free to stop me at whatever time you want to stop me, for how much ever longer you want to stop me. That way I can shorten, I can tune my talk accordingly. Okay, now the whole conference is on active matter, so I'm sure all of you know what active matters are. But just for the formality, I will again introduce what is active matter. So active matter systems are the ones which are characterized by an energy flux through them, and they are out of equilibrium. This is a well-known thing to this audience, so I don't need to elaborate it here. And as we all know that these kinds of active matters are there in nature at various length scales, right? Starting from a very small length scales of inside cell, what we have in motors and all, to these micron length scales, bacteria, to a larger length scales like bird, fish, and so on and so forth, right? But the point that we should know, and we know this also, all of you know this also, that these objects, right? For example, the bacteria itself, which is of micron size, right? The way they self-propel, the way they become active, okay, the mechanism of activeness is very different in different organisms. Even within bacteria itself, for example, the first movie, you can see the bacteria has a flagella. So it uses the flagella's folding, unfolding, which you all have heard so far, to do this kind of self-propulsion. Whereas the second movie is of a bacteria which doesn't have flagella, but still you are able to see this nice self-propelled motion, swarming behavior and all that. And therefore the flagellar folding, unfolding, which is the known thing in bacteria, will not work here, right? Therefore the mechanism involved for motion in such cases will be very, very, very different from the first one, even though it's the same organism, it's bacteria, okay? And similarly, at larger length scales, where the forces are very different, for example, at these smaller length scales of bacteria and motors, the viscous force is something that dominates. The inertial forces are extremely low. Therefore, the mechanisms are different there, whereas at larger length scales, the inertial forces also becomes prominent. Okay, and therefore, the mechanism of movement now will be different from the mechanism of movement here. Okay. So, but what is common in all of them is they all have this fascinating collective dynamics, okay? Some way or the other, they all are able to show this kind of swarming behavior, moving together behavior, cooperativity, and so on and so forth. And that leads to very interesting patterns in their collective motions, okay? Now, of course, based on, motivated by these naturally occurring motors, there is a lot of work which is being going on throughout, I mean, since centuries, to mimic these naturally occurring motors and make those motors in the real life, right? And people have been successful by making the big, big motors, right? Vehicles and all that. But when it comes to small scale motors, okay, this is a very recent phenomena which people have started synthesizing in the lab. Okay, maybe 20 years or 20, 30 years maximum is when people have started synthesizing these active motors at the small scale in the lab. And one of the pioneering work here, which I'm sure all of you know, is this kind of Janus particle, right? Janus particle, different shapes, different sizes, different properties that people are trying to synthesize in the lab. Here, what I'm showing you is a platinum, which is, sorry, a silica particle, which is coated with platinum, okay? People have worked a lot on the bimetallic rods, so where you have platinum gold, let's say, platinum, like a lot of other phenomena, a lot of other designs that people have come up with for this kind of Janus particle. Okay. Now, what happens in these cases is when you take these Janus particle, especially in the platinum coated one, and immerses it in a fuel, which in this case is hydrogen peroxide. Fuel, or people are, there's a lot of studies on the fuel also, what kind of fuel one can take, right? So for example, hydrogen peroxide is not very bio-friendly fuel. So one can think of more bio-friendly fuel. And there is a lot of work in that direction also to optimize the fuel. So, and make this kind of motor, because the ultimate one of the ultimate aim to design this motors is to use it for some potential application, and drug delivery being one of the potential applications. You would like to get them into your body, okay? And therefore, all these, the material that is used on the Janus particle, the fuel that is being used to propel them, all of them have to be more optimized, okay? So there's a lot of work in these kind of synthetic particles, okay? And where people are trying to synthesize and get the micromotors, which are of small length scales, okay? Now, one of the, as I said in the beginning, that when you go from a large length scale to small length scale, your forces changes, right? Inertial forces, which were dominant in the one which is at large length scale, becomes very negligible with the moment you go to a small length scale motors, right? And therefore, the mechanism that needs to come up, okay, should be such that the inertia is not there, so I will be able to move with a very high viscous environment also. And again, here motivated from biology, what people saw is in biological system, any biological system, small and scale biological system, the way to move was to break the symmetry. Okay, so the moment you break the symmetry there, okay, even if the inertial forces are very less, the objects are able to move in a very directed fashion for a long time. Okay, and that's what people are trying to do in the lab also. In various kinds of experiments, you just break the symmetry. For example, in Janus experiments, how do they break the symmetry? They break the symmetry by coating these silica particle, the platinum on the silica particle just by half, right? And what happens by that? The reaction that is happening happens only on one side of Janus, right? And what happens because of this reaction only on one side? There's an asymmetry of the product which is formed. Okay, and that asymmetry leads to the propulsion of the motor. Right? And there are other experiments where people are trying to break this symmetry by various mechanisms. Okay, one of the ways which I can immediately think of is where people have taken DNA itself from biology, okay, and they have synthesized these a pad track made up of microtubules, okay, and on that track they move this DNA, okay, this helical DNA, by bringing in some asymmetry, temporal asymmetry on the legs of the DNA. Okay, and that's way it moves. But the point is that you need to break the symmetry to make the particle move at that length scales. Okay, now this is another example. Okay, this is again there is a plethora of stuff that is there. Okay, these are objects which are rigid, which cannot change the shape. Right, now the next question could be, okay, what will happen if I change the shape? Right, so these are some work which people are trying to do, and this is what I will also take you towards the end, is what will happen if the objects that you're trying to propel, okay, has this property of shape changing. Right, for example, this is a vesicle. This is a synthetic vesicle made up of these kind of polymers, okay, but this is not a symmetric vesicle. It is made up of two types of polymerisome. Right, you can see this red type and a yellow type. Okay, these have different properties in terms of its permeability. Okay, and now inside this vesicle, these kind of enzymatic reaction where one enzyme, okay, changes the product, so the fuel to the product happens inside the vesicle, right? And because of this asymmetry on the vesicle, because of the difference in permeability of the vesicle at two different sides, okay, the product which is formed inside is ejected only from one side, from the back. Okay, and therefore this guy also shows a very beautiful motion. You can see that, right?
So essentially what you have here are micelles with different type of lipids. Am I right in understanding that?
Yes.
So where does the polymer come in the picture? Because micelle is only lipids, right?
So in the actual vesicle, it's the lipid, right? But this is a synthetic vesicle, which is not made up of lipids or micelles. It's made up of these kind of polymerisome. Okay, I don't really know the chemistry behind this, but what I understand here is the permeability of these two sites are different. So these are like polymeric vesicle you can think of, not the real vesicle. Okay.
These are self-assembled structures, right?
These are self-assembled structures. Okay. And then what happens is when you have the difference in permeability, the moment reaction happens, the product is able to come out only on one side.
Got it.
Okay, and then it propels. So it's fine, it propels. But the main aim of this paper was to find out what happens due to the shape change. Okay, for example, this is a rigid object. Okay, we know how long it will go. Okay, if it has a spherical shape, right? In spherical shape, what will be the velocity? What will be the directionality? Now, if I have the sphere changing to, let's say, ellipsoid, what will happen to its directionality? What will happen to its velocity? Will it be more efficient or less efficient? Those are the questions that was asked in this paper, right? So the idea was to change the shape, to get a particle which is able to change its shape while doing the motion, okay? And to find out how this shape changes affects the motion of the particle, okay? So this is one kind of shape-changing object that people have been trying to do. The other
one more question. Yeah. So the shape change, does it happen because of some applied electric field or something like that, or is it happening because of flow?
In this, yes, it's because of the flow most of the time. In this case, yeah. Okay. Now this is a case where it's not a vesicle; it's actually a polymer. Okay, and this is again a polymer which is assembled during the experiment. So the experiment they start with is genus particle, okay, metal dielectric type of genus particle. They put it inside this NaCl solution, okay, and apply the AC electric field. Now what happens when they have the electric field? Now this is an asymmetric particle, right? Now because of this electric field, the surface charge which will be produced by applying the AC electric field would be different on two different sides, right? Therefore, the counter ion which is there in the solution, okay, their condensation, their dynamics is going to be asymmetric, right? And you have a asymmetric field around this genus object, and this will show a very nice self-propelled motion, okay? But interesting part of this paper was that they could show that by tuning the frequency of the AC electric field, the strength of the AC electric field, these genus particles not only self-propel as an individual entity, they are able to self-assemble into various types of structures. Okay, these elongated chains, the rings, and so on and so forth, right? And chains also of different sizes. And these also move. You can see that they move. There's a free forward chain, that is what they call. So depending on the assembly, they will have a type of assembly such that they will move. They'll be able to move in a particular direction. And if you fix one end of those particle, okay, it is able to show this kind of cilia-like beating. Okay, which is there on the cells. Okay, many of you are from biology. You know that we have cilia on our body, which are the active polymers only. These are like microtubules with motors working on it, and because of this activity, the cilia actually does this kind of oscillatory beating motion. Okay, and here they were able to show that once the chain is formed at a particular frequency, okay. And if you clamp one end of the chain, okay, this is like an active polymer. This is like a cilia and shows this kind of beating behavior. Interesting, right?
Two or more of these chains, and we clamp those chains, linearly like this. And do they also exhibit like synchronous oscillation like cilia?
In this experiment, they have not shown it, but I will show you that when in our work we can show that this kind of active polymers will also show a synchronization. And why does the synchronization happens and all that I will come to. Okay, fine. Okay. So the idea here to tell you in this slide is that these active particles are of various kinds, various shape-changing ones are the ones which I'll be focusing on, especially on the active polymers is what my focus will be in this talk. Yeah.
How do they form chain?
Okay. Okay. So you can see here, right? You have these metal and dielectric genus. Okay. Now, when you apply electric field here, the surface charge which will be generated here would be different from here, right? Therefore, the counter ion condensation on this side will be different from this side, right? And therefore, they will all have a particular direction of motion, right? And when many of them come together like that, they will make a chain. And the moment you switch off the electric field, these chains will disappear. Okay? Okay. Yeah. How are the circular chains formed? Okay. So that's also very nice thing to see. You can see that there is a distribution of the structures which are present here, right? And the chains that are also formed, okay, they are all, because they are subjected to fluctuations. They are in a solvent, right? So it's not that all of them will be like this. the solvent will try to change their orientations also. Okay, and that way some of them which are small will be in a straight configuration, but the one which becomes longer, okay, because of this fluctuation, which they will try to orient in different direction. Okay, and once two ends come close to each other, they will close and they will make a change. Yeah. Okay, so first of all, this is not our experiment. This is the experiment done by this group. And what I could see in this paper is they can actually go till 15, 20 beats or so for a particular linear chain. AC electric field, the frequency and strength of the AC electric field, and also the concentration of the NaCl solution, because that provides the counterant.
Okay, so because once you turn off the field, the particles are not in that conformation anymore,
Correct,
right?
correct. Right? Okay. So, I think I'll have to. Okay. Fine. Now, in all these type of experiment, one thing is very common. Okay, of course, there are many common things, and I'm showing you 3 different types of experiments. Okay, for 3 different materials. For example, this is, you can see, is a mixture of active and passive genus colloid, active and passive colloids. Okay, some of them are active. The ones which you can see is a black and white. These are genus active colloid. The ones which are white, those are passive colloid, right? And this is a bacterial motion, and this is a motion of the microtubule and motor protein mixture, right? In all of them, here also you can see these kind of collective motions. Here also you can see these kind of collective motions. Bacteria are known to swarm and all that. So there are a lot of things which are common. They are all active is one thing which is common. They are all at similar length scales is the second thing which is common. And the most important thing which is common in all of them, which I will be concentrating on, is they are all having solvents inbuilt into it. So the solvent property, having solvent which will induce a lot of effect not to this system, okay? And what we would like to explore is how do we put solvent in our computer, okay? So how do we simulate this system with the solvent into it? Because solvent is an important quantity, important parameters in all these systems, okay? It's very, very, very important. And most of the time in physics, we ignore it because we will not be able to handle it properly, and we put an effect of the solvent in the models, okay? Most of the physical models which has come in the past will have the effect of the solvent, okay, some implicit effect of the solvent like fluctuations and all that, but they will not have inbuilt solvent into the model. And I'll show you that having those inbuilt solvent will affect the dynamics a lot. Yeah.
Can you explain in second and third case how solvent is playing role in making it active?
So solvent plays a very important role. Solvent may not play a very important role in making it active. Okay, activity could be inbuilt. For example, in this case of, by the way, bacteria needs a medium to survive, right? And that's a solvent medium. Okay, so that way the medium is there. Okay, you cannot remove that. It may not need the medium to propel. Okay, but it will need the medium for the collective motion. Swarming and all that is hydrodynamically driven most of the time. Also here, okay, these kind of collective swarming, swirling motions and all that which is there, okay, it could be that solvent plays a very important role there, right?
Please use it.
So hydrodynamic interactions are the one which will play a very important role in the collective dynamics of all of them.
I would assume the solvent influences the nature of motility, and is that what you're trying to, when you say you incorporate actual solvents and not just its effects, is that what you're
I'll tell you how what all things it is going to affect.
So another aspect of solvent is that in many of these cases, these are electrolyte solutions, right?
Yes, yes.
So, but you are not going at that level, and you are just assuming this is some kind of a background fluid,
Correct,
which is exchanging momentum with the system, and
correct,
that's it. Okay.
correct. Okay. Now, how do we deal with these kind of system in computer? Okay, that's the question that many of us ask, right? How do we deal with it? And one of the ancient way or the most classic way is the molecular dynamics. Classical, I'm talking about classical MD right now, okay? So we solved Newton's second law for all of them, right? And what is this Fi? Fi is the total force that all of them will be experiencing because of all others, right? And how is this Fi calculated? So you will have, for every particle, you'll have some potential, right? And potential will come, why will it come? It will come because of the internal interactions. Internally, particles will interact with everything. So for example, colloid with solvent, okay? So I'll have colloidal particles which are going to interact with all the solvent, right? Solvent particles which are going to interact with all of them. So you will have some sort of a potential energy, some form of potential which you are going to put in, okay? And then there can be some external forces, external potential also, that will give me the total potential. And with that total potential, I'll get the force, okay? And that is the force which is used to evolve the system. Okay, and that's how in simulation, in classical molecular dynamics simulation, that's how people evolve the system and get all the properties of the system, whatever properties that you can think of. This is how people can. So I'm very, very, very basic of how we do molecular simulation. Now, yeah.
As you have taken that Fi equal to minus of grad of V, right?
Right.
So that means the system is conservative. So, I mean,
Yeah,
is
I'm
there?
not talking about the non-conservative system.
So
right?
there is no loss of energy.
I mean, classically, if it can happen, loss of energy can happen, then you have to add more terms and all that. But this is the most basic way of thinking of how, and this is exactly, this is, as I said, for people who don't know how to do anything in the simulations, in the computer. Okay, so let's say I want to model a polymer and solvent in the simulation. What do? I take these particles, monomeric particles, put some potential between them, right? Neighboring potential, the non-neighboring potential, their interaction with solvent, right? So all these things will come in V, right? And then we will have, we will evolve them using this.
Okay.
That's all I wanted to say here, okay? Now, but in the actual experiments, it becomes, when I want to put in the solvent, okay, there's a huge gap of length scales. Okay, for example, colloid with the solvent that I showed you, right? you can see that there is a huge gap of length scale between the colloid and the solvent. Right? Colloids of the order of few nanometers, 10 to 100 nanometers, right? Whereas solvent is of the order of 0.2 nanometer, let's say. Okay. Now, if I want to simulate them using a classical approach, right? I will go to the smallest length scale, which in this case is solvent, okay? And then do a classical MD. So that means I have to go to this kind of length scale, starting from this length scale, and the time scale also, which is important, right? The characteristic time scale, if I want to find out for colloid and solvent, okay, this is the diffusion time scale will give me the one of the characteristic time scale, which you can see for the colloid will be of the order of few microseconds, whereas in solvent it will be of the order of few picoseconds, right? So if I want to do a classical approach, classical MD, then it's very, very inefficient way, because in classical MD, what will I take this, my unit of scale, length and time will be the unit of solvent time scale, because that's the smallest one, right? And then I will have to go to that kind of larger length scales of incorporate the colloid, okay, which is very, very, very inefficient if I want to incorporate the solvent using a classical MD approach.
Ma'am, is A the radius of the particle? There, the 2 dt is
2 dt, yeah, A is the radius of the particle, right? Correct. Okay. So, so
can I
there
ask
is
a
this
question?
bridging. Yeah, sorry.
Sorry. So, were you answering or?
I answered. I think she said, what is A? A is this or the size.
My question is that, so if you are trying to consider the hydrodynamic effect of the solvent, why do you need to consider the solvent explicitly?
Okay, it's not only the hydrodynamic effect that we would like to incorporate. Okay, also if I, let's say, want to model this chemically active thing where the chemistry is also involved, right? To involve the chemistry, I need to have the solvent.
In that case, you also want to consider some structured solvent where
that can be a next step, but right now a simple solvent with the chemistry involved is what I would like to do. Right? And then just having a simple hydrodynamic sort of Navier-Stokes will not help me, will not be able to bring in. Okay? Fine. So I need to have some method which bridges the length scale and time scale.
The characteristic time here represents the kind of relaxation time.
Some sort of a diffusion time scale you can think of, because how I'm calculating this is by this 2 dt is equal to A square, which is your diffusion equation, right? So, and then you estimate some diffusion time scale for this from this.
Okay.
Okay. Yeah. Any other question? Okay. So what do we do if I want to bridge this length scale and time scale gap? One way is to neglect all the non-relevant function of the solvent, and take only what is important for the fluid properties, right? And what is important for the fluid properties is, as we said, structure of the solvent. Okay, structure of the solvent in many of the time may not be relevant. Okay, but solvent being present and carrying out these reactions, H2O2 going to H2O and O2, changing their characteristic is important. Right? So how does the H2O2 looks? How many atoms you have in H2O2? How they're arranged? That may not be important. But the H2O2 is changing itself to water and oxygen. Okay, is important. Right? So I can omit that kind of non-relevant functions here. Okay, and take only what is important for us. Right? For most of the time, which we think, what are the fluid properties that is important for thermal fluctuation? So we must have a model which incorporates thermal fluctuation, but there are many such. Okay, why am I talking about a special one? I'll tell you. Okay, so my model should incorporate thermal fluctuation. Okay, should incorporate hydrodynamics, should be able to give me these kind of changes if I am interested in these kind of chemical reactions. Okay, so those are the important properties of the fluid that I am looking for. Right? Or any other coarse-grained simulations look for by bridging this gap, right? So what they would like to do is, most of the time, the importance would be on thermal fluctuations, the hydrodynamic interactions. Also in biological system, we have this spatio-temporal forces, right? Which is different. In biological system, we have forces which are coming up, going down, going back, right? Those are the things which will be important, right? So any of the coarse-grained method should be able to incorporate those things, and we'll leave out the rest of the stuff. Yeah.
The number of the solvent molecules is not conserved.
Number of the
typically.
solvent molecules in this case is conserved. In our case, is conserved. It will be
If you have
conserved.
chemical reaction,
Hmm?
but if you have chemical reaction.
If you will have chemical reaction, yeah. So there are, so this method itself, which I will talk about for conserved solvent particle, one can also do a reactive MPCD where you can bring in this kind of changes in the number of particles. Okay, right? But I will not go into that in today's class. Okay, right. So the key issue to resolve in all these coarse-grained simulations are to find out the interplay between thermal fluctuations, hydrodynamic interaction, and as I said, in many of the system, you have the spatio-temporally varying forces. So we have to resolve this, what becomes important at what level, and so on and so forth. And there has been a lot of work to develop different types of coarse-grained simulations in the literature. Okay, so it starts, actually the coarse-grained simulation by incorporating the solvent and all that, those had started with, which is basically a generalization of Navier-Stokes only, or most of them are generalization of Navier-Stokes only, started with lattice gas automata. So what they said, okay, my particles, my solvent particles will be arranged in a lattice, okay, and then they will evolve from lattice to lattice, and then the collision between the solvent particles will happen only when they hop from one lattice to the other lattice with some probability. Okay, so what is when we are talking about the fluid? So right now you forget the colloid and all from your mind, but just think of the solvent. What we are trying to do is to model a solvent. Okay, and in all these coarse-grained approaches, most of these coarse-grained approaches, be it lattice gas, or it's DSMC, direct simulation Monte Carlo, or the multi-particle collision dynamics, the idea is that the property of the solvent that I'm going to take is that the solvent is going to move to its mean free path, okay, and then it's going to collide. Okay, I will not put any other details, and you will see that just by doing that, you can actually get the solvent effect beautifully, right?
Yeah. So just a clarifying question. So in MPC, are you trying to solve the Boltzmann equation?
No, I'll tell you what MPC is. Yes. So that is done in lattice Boltzmann.
So when you say the solvent molecules like hop from lattice point to under, so are you taking the length scale of the solvent, the characteristic length scale of the solvent as the?
It may not be the characteristic size of the solvent. It could be the mean free path of the solvent. Right? So we have to think of some characteristic scale. I'll come to that also for the MPC. So that is the lattice is there for these two methods, lattice gas automata and lattice Boltzmann, but for all other methods, these are non-lattice models. Okay, you have a continuous position and velocity of the particles. Okay.
So this lattice model, so there's a polymer theory which, like the Florehagens, is it similar to that?
I don't know that theory right now, so
okay.
I will not be able to comment it. Okay. Maybe I can discuss that with you later. Okay, so this is what I'm going to concentrate on, one of them, which is called multi-particle collision dynamics. And this model was developed by Capral and co-worker in 1999. So you can see it's about 25 years now from now. And it's a particle-based method similar to DSMC. So I should tell you what DSMC is. Now in this DSMC model, which is an MPC is an extension of DSMC, they consider the fluid to be particles, which is there for all the, whether it's lattice gas or DPD or whatever, right? So you have these fluid particles. So you don't have the effect of the fluid, like in Brownian dynamics, right? In Brownian dynamic simulation, we put a noise term, okay, which brings in the effect of the fluid. But in all others, you have fluid particles. So you have a fluid particles which evolves, which ballistically moves for some time, okay, and then it collides. That is what DSMC had, okay, but it ballistically moves for some time and then it collides. But the collision in DSMC was much more involved, time consuming, in the sense that there each pair of particle was colliding with each other, right? Each pair of particles. So even in DMC, so let's say this is your entire box, entire simulation setup, entire experiment setup, let's say, okay? Then all these particles, solvent particles, ballistically moves, okay, for some time. So that means in that time, they don't see anything else, right? Even if something is coming in their path, they don't see that. They ballistically move, and which is realistic also, because we have this kinetic theory which says that up to the mean free path of the solvent, it is going to move ballistically, right? So this is very realistic. And after some time, which is your characteristic collision time, okay, these particles in DSCMC, in this simulation method, they are sorted into small cells, okay? And within the cells, why cells? Because the collision also does, so the particle here will not collide with the particle there, right? So there will be a range of collision between the particles, okay? So that is what, that is why these small collision boxes are formed. And within these boxes in DSMC, each pair of particles will collide with each other with certain probability, okay? And that probability depends on the velocity of, relative velocity of each pair. Okay? Yeah.
You can choose the size of these shells.
This size of these shells are mostly their system units. I'll come to that. Okay, I'll come to that. Okay, I'm just trying to tell you what DSMC is right now. Is it clear what DSMC is? Okay, so based on this DSMC method, Kapral and co-worker had come up with this modified simulation method, which we know as, there are various names for this. You can hear this as MPC, right? MPCD, multi-particle collision dynamics, right? Or people also call this to be SRD, stochastic rotation dynamics. Few groups also call it to be real coded lattice gas, and so on and so forth. But the most common name that we hear of right now is called multi-particle collision dynamics, okay? And this kind of dynamics actually is beautiful. It conserves mass, momentum, energy. I will show you how, okay? And of course, it has a full hydrodynamic equation. People have solved this, not only Kapral, there's a huge amount of literature which is available now, and it has this intrinsic thermal fluctuation. That also I'll tell you how the thermal fluctuations are taken into account. So this is something which is a very, very, very nice model of incorporating solvent into the system. If you are interested, you can go back and see these reviews, which is very comprehensive.
Ma'am.
In fact, yeah.
Yeah. So here, like you are taking those collision cells.
Yeah.
As you told, like, okay, the first one won't, particles won't be colliding with the last one. But the particles in that has a probability to collide with the next cell. So, but when we are defining boundaries for the cell, it will be like limited, that inside ones only collide with each other. So what about the particles at the boundary and the
I'll come to that. That's a very good question. I'll come to that in the next couple of slides when I will explain you the MPC. Okay. So what is this MPC algorithm? Okay. So you have endpoint particles. Okay. Think about, there's no size of the particle, the solvent here. Okay. Size of the solvent is irrelevant. You consider all the solvent to be point size. Okay. Why this is a valid assumptions? Can you think of it as why it is a valid assumption?
Size of these particles are much more smaller than the solvent.
So these are solvent only.
Sorry,
solute. Okay. And then even if there are, of course, at very, very, very small level, these have some sizes. They will have overlaps and potentials and all that. But those are very, very, very small, and we can actually ignore that. And therefore, we can think of them as endpoint particle. Okay. They will have, this is not a lattice model, as I said, they will have their continuous position, velocity, and a discrete time increment, which I'll tell you what it is. And then this algorithm is done in 2 steps. The first step, as I said, is called streaming step, where particles move ballistically. They don't see each other. They don't see the existence of others. They just move to ballistically up till this streaming time, which is called h, which decides the mean free path of the system. Okay, and then at the collision step, so you do streaming till h, okay, and then you stop and you have to collide. The solvents have to collide. Now in this collision step, they are sorted into these collision boxes, okay, and they interchange the momentum within the box itself, within the particle of the box itself, okay. And how do they do that? Not like DCMC, the direct simulation Monte Carlo, where you had taken the pair of the particle. Here, the particles are not going to collide with any other particle. They will feel the other particle through the center of mass velocity of that particular cell only. Okay, so that way it is much more coarse-grained than DCMC, right? You don't really, any of the particles don't see the other particles as such, okay? But in the simulation box, in the collision step, what they see is the center of mass velocity of all the particles in the cell, okay? Now then what happens? By this center of mass velocities of all the other particles in the cell, okay, we rotate the velocity of each particle relative to the center of mass. Okay, so relative velocity of the center of mass of the particle with respect to the center of mass is what is calculated, and that is what is rotated by this random rotation vector, okay, to get the new particle velocity.
Two questions. So basically this update rule is quite similar to what we see in the Vichek model, right? And the second question is, how exactly do you define the box size? Maybe you are going to come to that at a later moment. Because if it is too large, then you are basically covering the entire system. If it is too small, they are considering only a very few people.
Okay.
And how do you consider that in a periodic boundary condition?
Okay. So I'll come to all of them one by one, but maybe just to get you this thing. This in Vichek model, what happens is all of them, it is very similar to that particle try to align through its neighbors, right? So you take all the neighbors of the particle, you calculate the center of mass velocity, and then you put a force to align in that direction in the Vichek model. Here, it's not the alignment as such. Okay, so what you do here, let's say this diagram will make it more clear. Let's say this is my particle velocity. This is the center of mass velocity. I got the relative velocity of this. Okay, then I rotated that relative velocity by this random rotation by an angle alpha, right? And then calculated the updated velocity of the particle by summing this rotated velocity with the center of mass. So there is no alignment which is happening in Vichek model. What is happening by doing this is the particle is with respect to the center of mass velocity of that box, okay, is trying to achieve its velocity, trying to match the center of mass velocity. So by doing that, what happens if I am a fast particle, okay, and with respect to all my neighbors, I will try to slow down, okay, and if I am a slow particle, I'll gain the velocity in that by this. But I'm not trying to align, which is the case in the Vichek model. Okay, is this algorithm clear? Yeah.
I'm a bit confused about like these points represent the solvents, right?
These points represent the solvent.
So like, I mean, how many number of these points, like you
Millions.
have this?
Millions will be there in this whole box. Okay, and then in small cells, you will have maybe hundreds or thousands of them. Yeah.
So I have confusion with this angle alpha. So I don't know simulation. So how do you take this alpha? Because I can rotate
any angle, right? So alpha is the angle that is a very important parameter of the system, and that decides a lot of transport properties. I will come to that. Okay, so you choose an angle. Okay, you choose an angle right now. Okay, and then you rotate by that angle. Okay, by this random rotation. okay, this center of mass velocity. And this is an important parameter of the system. I'll talk about the effect
you
of
said
alpha
you
also.
rotate, right? I mean,
I'll rotate.
so rotation in which direction? I mean, if it is a three-dimensional case, so my confusion
so
is.
This is a rotation matrix.
Right.
Right. So in 2D you will have sin alpha, cos alpha, cos sin, and sin alpha, cos alpha. So you take that matrix, rotation matrix, and rotate this center of the relative velocity with that.
And
alpha is a parameter that you will choose. You can choose 10 degree, you can choose 100 degree, you can choose whatever.
It is stochastically.
Yeah, yes.
And
I will talk about that also, how to choose alpha.
Okay, and you update all the particles inside a single.
Correct. So let's say I have 100 particles, 1000 particles here. If I would have gone by the DCMC calculation, where we have to choose each particle and then rotate the velocities of the pair, then there'll be huge number of calculations. Here I have to just do 1000 updates here. Right? For each particle, what I need to know is the center of mass. I don't really need to know what my neighbors are, where each of the neighbors are doing. What is the center of mass? And then based on that center of mass, I'll be able to get the updated position. Clear?
So this is the center of mass of each box?
Of each box.
Okay. Okay. So I is the particle index.
I is the particle and that is associated to a cell Ci, okay, or a collision box Ci, okay, and center of mass is the center of mass of each of the box here. Okay, maybe that's why it is getting confused here. No? Yeah, so I index in this case means the I that we are interested in which box it is. That's all.
Ma'am, will the velocity distribution be Maxwellian?
Yes, that's the beauty of this whole simulation, that it goes to a Maxwellian distribution, the equilibrium. Yeah. Huh? This is in 2D or 3D?
Yeah.
It can be done in both. Okay, you have to just choose the rotation matrix accordingly. Okay, any question on this?
Ma'am, as we are choosing this rotation stochastically, so, and you said that the particles are trying to like align.
Speed up? No, not align.
Okay.
Speed up off or slow down based on the neighbors.
So how this rotation, like rotation is stochastic and they are matching their velocities to
stochastic in the sense of when I hop from one cell to other cell, because this is going to change. But within a cell, all of them will have the same rotation. Within the cell, okay, which is a small part of that whole box, okay, I'll have the same rotation for all of them. Okay, and stochastic, why the stochastic? Because this rotation is not same for all of them, all the boxes.
Okay, so this is not only one particle velocity we are moving with R alpha, it's like rotation of the whole cell. Is it?
No. R alpha is something that I will choose for a small cell. Okay, and all the particles will rotate by the same R alpha. I'll also rotate by this, the other one will also rotate by that, so it's not stochastic. But when it comes to rotation of one particle in this cell and the other particle of this cell, the R alpha are not correlated. R alpha is not correlated.
Yes. So how that thing that all the particles wants to get the same velocity as VCM? So
that is coming because what you're doing is, so you see this, okay? So what is happening is your VCM, okay? So you have this relative velocity of the particle with respect to VCM, okay? And the final velocity that you have got, okay, is sum of VCM and this relative velocity. Okay, that is how it is trying to achieve that center of mass velocity.
Okay.
Maybe we can discuss more if it's not clear. Okay, so I'll go quickly. You can actually show that this kind of collision step, this is also very important thing that was shown. In this kind of collision step, actually you can show that this conserves momentum and this conserves energy. So by construction itself, right, this model is one which conserves all the quantities, mass, momentum, and energy. One can also do some tweaking and conserve the angular momentum, but by far whatever I have shown conserves mass, momentum, and energy, not the angular momentum. Okay, now coming to rotation random rotation that you all were confused about. So what do we do in these random rotation? We choose alpha. Okay, alpha is the angle that I choose, which is my system parameter. You will see that that affects a lot of stuff. Okay, but a particular cell can take plus alpha or minus alpha for the rotation. Okay, and this is my rotation matrix, right? Simple rotation matrix which I carry out individually in each of these cells, and the rotation angle alpha is fixed for one box, one cell. Okay, but that can be different for any of these cells. That is not equal in the neighboring boxes, and that incorporates your thermal fluctuations, right? Okay, in 3D we have more options for the same alpha, plus alpha and minus alpha. I have 3 directions also, correct? I can choose alpha x, my rotation matrix would be like this, minus alpha x rotation matrix would be like this. So I'll have 6 options. I can choose any one for any of these 3D simulations, 3D collision boxes.
Ma'am, but alpha is different for each cell, is like magnitude is same, like alpha angle is same, but the direction of rotation is different.
So the rotation matrix that you are using, okay, is different for different cells.
Okay.
Alpha is the same, okay, but the rotation matrix which I will use, okay, to rotate the VI minus VCM is different for different cells.
And alpha we choose like some random number.
So alpha, as I said, alpha is a system parameter. I'll come to the effect of alpha also very, very quickly. Okay, right. So, and this is one of the method. Now what people are trying to do is choose a random rotation, a random vector also. Okay, instead of choosing out of these 6, you choose a random vector. Okay, by creating the random points. Okay, a random variable, two random numbers you choose. Okay, create a vector, random vector from that, and then rotate by an angle alpha along that random vectors, right? So by doing that, we introduce less anisotropy because you have more options now. Okay, instead of using this R as these specified 6 ones, you choose any X random vector. Okay, and about that you rotate by an angle alpha. Okay, and this is the one which is most extensively used nowadays. Okay, so rotation is clear, the algorithm is clear. One thing which is important here to realize that this is not it. When in 1999, Capral proposed it, this is how they had proposed it. And later, around 4 or 5 years later, people realized that this algorithm actually breaks down the Galilean invariance, right? And what is Galilean invariance tells me that if I have a system, whether it's moving with 0 velocity or is moving with some velocity, the system should be identical. It should not change, right? Whereas if I see this, okay, and if I see a system with 0 velocity, okay, you see the environment of these 2 red particles, and the same system with a non-zero velocity, the environment is different, okay? And this is more prominent, okay, if the mean free path of these particles is much smaller than the choice of the cell size. If my cell size, this size of these boxes, if mass is much larger than the mean free path of the particle, then what will happen? The particle will be in the same box, same collision box for a long time, right? So that means what? It is going to collide with the same set of particle for a long time, correct? At 0 velocity, let's take the case of 0 velocity. If I take this red particle, which has a very small mean free path as compared to the box size, okay, it is going to stay in this box for a long time. And that means it's going to see the same neighbors. So its velocity will be correlated for a long time. Whereas the moment I put in a velocity to the system, V becomes non-zero for the system, right? This correlation goes away. That means my Galilean invariance is broken down. Okay, and therefore there has to be some modification.
Invariance actually leads to momentum conservation, but your system already conserves momentum.
That's right, but it also tells you whether the system is at rest or moving with certain velocity v. Okay, the system should behave identically. Correct?
Yes.
Right? But in this case, let's assume a case, let's take a case of a particle which has a very small length scale. Okay? This system will have, because it is going to see the same neighbor all the time, it has not moved out of a box for a long time. Okay? It will have a correlated velocities. Right? But if I move the same system with some velocity, v, okay, that correlation will go away. Right? So even if my conservation laws are there by constructions, but this kind of artifact will start coming in. Correct?
May want the system also include the set of grids?
Set of?
The grids, the grid we are choosing, the box. Is in that also part of the system? I mean, when you say when you move the system,
so you're giving a v velocity to all of them.
Yeah, don't you have to do that for the box also? No,
no I mean, box in this case is something which is defined by the particles only.
Okay, okay.
Right?
Okay.
That's what, so box, as such, the box would mean the boundary in which the particles are.
Yeah, okay.
Okay, so now then people, so you can see that after 2 years, this was realized, and Hale and Kroll actually came up with a solution, and their solution is pretty simple. And what they do is they tell that why do we have to take this black box all the time? Okay, during the collision step, I can randomly shift the black box. Now, by shifting the black box, I mean shifting the particles. Okay, right? So I can take up all the particles, randomly shift them either in this red grid or this kind of red grid or this kind of red grid. So I will at the collision step, I will do a random shifting of all the particles, either horizontally in the plus x, plus y, minus y, plus z, minus z at a given collision step. Okay, and what will happen because of that? This random shifting will actually now randomize the positions of the particle. Right? So this Galilean invariance problem that I was talking about, now whether it is V0 or V non-zero, randomization has happened. Okay, and therefore this breakdown of Galilean invariance is no more there. Okay.
I'm just want to ask, like the addition of extra velocity in the center of mass of the entire box is coming due to the error in the rotation matrix scheme, right? I mean, the small boxes are not self-averaging out to be 0, right? Something like that.
This why are you calling this to be an error? That I don't understand.
No, the addition of extra velocity, the entire system.
Addition of extra velocity, this one that you're talking about, where I said this one.
Right.
This is not the addition of extra velocity. This I am saying that you take the same system. Okay, if I give it a homogeneous velocity to the whole system,
the entire box,
external,
right?
External.
Why this is appearing? Because there is.
This is an external velocity that you can put in the system. Okay, an external. I will not say the force, because that will take the acceleration. External homogeneous velocity that you can impose on each of these particles. Then this system and this system is not same in the original MPCD.
Okay, I think we can discuss it later.
It's not the center of mass being non-zero. Overall, you have the momentum, which is okay.
Ma'am, this random shifting scheme will probably not work for. So it will probably work only for periodic boundary condition.
You are right. It will work for the way it was proposed was for the periodic boundary condition. But then for wall type of boundary condition, there is some proposal or there is some work where they take these ghost particles, okay, and then do the random shifting and all that. So that kind of random shifting has been done with this kind of particles also. Okay. So right. So by doing that, the Galilean invariance is restored. Okay, there is the isotropy. Now you have the system is more isotropic because you are randomizing it much more. And another very important point is collision transfer is enhanced now because you are randomizing more and more. Okay, the neighbors are randomized more. Therefore, the collision transfer will also be enhanced by doing this. Okay. Now, I just said this in maybe 1 hour, this whole thing, but this story, as I said, is been going on for 25 years. There are a lot of work, lot of groups across the kind of globe which are working on this kind of this model on the theoretical on theoretically establishing this model and have shown that the conservation laws hold. Phase volume also phase space volume also remains conserved. This particle single particle distribution function is a Maxwell-Boltzmann distribution function, which is talked before. This has the H theorem which exists for this. So I'm just pointing out this whole thing, and if you are interested in any of them, you can go through the papers and the review which I have talked about. All of them gives in detail how all of these points are coming into picture. One of the very important point, the calculation of transport properties in this system is actually very analytically, it is done. And as I will show you for one of the transport properties, the simulation also gives a very good match to the analytical result which has come for this particular method. Okay. Hydrodynamic flows for known systems, for known analytical results. Okay, this system actually beautifully matches the hydrodynamic flows which are generated, and therefore people now have a lot of confidence of taking it forward to an unknown situation also, where flows are unknown, and with a lot of confidence people can say with this model, okay, this is how the flow will look like. Okay. Now, units and parameters which are important for any of the simulation method, which I said, the mass, for any simulation method, we need to talk about unit. What is the unit? Because these units will help us correlate with the experimental data, right? So the unit in this case is the length unit is the box size. Okay, box size decides what is my unit of length in this case. The mass unit is the particle size, and the energy unit is the kBT that we put in here. And then one can actually construct by these three basic units, mass, length, and energy unit, the time unit, right? So these are my system units. And then by parameters, as I said, the collision time is something that decides the mean free path, okay? And that mean free path is related to the size of this box also. So the size of the box actually is chosen to optimize the calculation of H, so that we are not very off from the mean free path in this particular case. If my box size is very large, okay, then mean free path will become accordingly very small, and all those. So, and in fact, this Galilean invariance which I was talking about, breaking down of that is more important when you have a very small mean free path. Okay, so therefore, if I have this H such that mean free path and A are of the same size, okay, then actually you don't need to do that kind of random shifting. So those are the things that one can keep in mind while doing the simulations. And this H, collision time, the rotation angle, which we have understood hopefully so far, and the, sorry, this is not system temperature, it's the system density rho. Okay, density of number of particles. These are the three system parameters that we have. And these system parameters actually decides the transport properties of the system. Okay, so these are the three system parameters, and size of the box, of course, finite size effect and all that will be decided by that, but that's not very important here. Yeah.
Density determine the temperature if I look at it. So rho was n by the box volume, right?
Correct.
And you say that is equivalent to temperature. I am just
no, that's what I said. That's wrong.
Okay.
That's my mistake. That's not system temperature. That's the system density. I'm sorry. Yeah. Okay. Now, with these system parameters, analytically, people have calculated all the transport properties, like viscosity, the diffusion coefficient, and all that. One of them, which I will just show here, others you can see in these papers. Right, the people have actually tried to have calculated analytically the viscosity of this system. Okay, and viscosity will have two parts, the kinetic viscosity and the viscosity due to the collision. So viscosity is what? The amount of measure of the momentum transfer, right? Momentum transfer happens both in the streaming step as well as in the collision step. In the streaming step, I carry the momentum with me, okay? And then the collision step, I collide with the other particles and find out the, transfer the momentum in that step. And these two contributions of viscosity can be calculated, and you can see that both of them will depend on these kind of system parameter A, H, rho, alpha, and so on and so forth. For example, if I want to understand, let's say H dependence, right? H was my collision time. Larger is the collision time, that means more ballistically for more time I move ballistically, the contribution in the total viscosity will be more from the kinetic contribution, right? Less from the collision contribution. But if I collide more frequently, that means my H is small, the contribution in viscosity will be more from the collisional term. Okay, and this is how the kinetic viscosity will go as a function of alpha. This is how the kinetic viscosity will go as a function of H, right? So alpha and H are my system parameter, and you can see this red one is the analytical calculation from this, and this combination of these two, and these dotted ones are from the simulation. You can see a very good match between the analytical expression for the viscosity and what you get from the simulations, and that depends very much on this alpha and H, on this system parameter. One last thing, yeah.
A little doubt. Like the particle from one cell can go to other cell?
Of course. So because you're streaming, right? How you're doing this whole thing? There are all of us, let's say all of us move, right? And all of us are moving randomly. We are all not moving in the same direction. Okay. So for some time I am moving this way. Okay. And then I stop. You might have moved from a different cell, okay, to the same cell where I am in. Okay. And when we stop, we are in the same cell. And then we collide with each other, change our velocity. And then I move in a different direction. Okay. And he comes in that same cell. Okay, so my environment will change. So these particles will continuously change their boxes in all the collision steps, right? But if I move very slowly, or my collision time is very large, right? Then for a minute, my mean free path, all those parameters, right? It may happen that I'll stay in the same box for some time. Okay.
The cell dimension, is it possible?
Yeah, it can happen because your mean free path depends on your H collision parameter. Okay, it can happen. Okay, so as I said, to match the results from the experiments, you need to really know the system units, and another important thing that we need to do here is match these dimensionless numbers. Some of the dimensionless number that we all work with, Reynolds number, Peclet number, Schmidt number, and all that. Okay. Now, the MPC, in the MPC, usually the Reynolds number range is of the order of 0.1 to 10, and similar range for Peclet number also. And Schmidt number is something which is what I'm going to show you here, which is the ratio of momentum transport to the mass transport. And the Schmidt number is of the order of 1 for gases, okay, because mostly the mass transport that happens. Whereas for liquids, because it collides a lot, it will have a Schmidt number which is of the order of 100 to 1000, right? And you can show that you can in MPC by tuning your system parameters, which is alpha and rho, right? For different H values, these are the 3 system parameters I told you, right? Alpha, H, and rho, right? By tuning these system parameters, I can tune the Schmidt number, and depending on what is my fluid that I want to work on, whether I want to work on in the gaseous regime or work on in the liquid regime, I can choose any of these and go to those regimes. So this is a wide range of Schmidt number is something that is given in this, is achieved in this simulation.
Ma'am, you said that use a Maxwell distribution here. So where does that come?
Maxwell distribution? Okay, that I did not show, but once you will do evolve this system, you will get the final velocities of all these particles, get a distribution of those velocities, you will get a Maxwell distribution.
Okay.
That will happen.
So
I sort of understand how alpha and rho, not alpha, but rho can control whether some system is a liquid or a gas. But it's not clear to me how H, which is the time step, right, essentially, how does that control whether
So
something
let's
is
say
a
my
liquid or
H is
gas?
very large. What does it mean? It means that the particle moves ballistically without seeing others for a long time.
Right.
So
Okay.
which one does that?
So that
Gas.
will be a gas.
Yes.
Yeah. Okay. Got it. And what about alpha? So why alpha large?
Okay. Alpha small, large alpha is, that means all of them are rotating a lot.
So basically it's
Yeah.
highly fluctuating. So
Yes.
it's like a gas.
Yes. Highly fluctuating would be, will be liquid, no? H alpha large, that means you're rotating by a large amount. Your velocity is rotating by a large amount. The small rotation will really not change.
I see. So the collision
Collision
is much.
time is
Okay. Okay.
Okay, shall I move forward? Okay, fine. So this is, now that was about whatever I have talked to you about is for single component, right? But this is a beautiful method where which can be utilized, which can be utilized if you have multi-component also, right? Instead of one type of particle, you have two types of particles. Yes, yes. Okay, so if you have now more than one type of particle, right, then what do? We can actually now modify the method, okay, and distinguish between alpha A and B. Okay, so basically now you calculate the center of mass velocity of one type of particle, calculate the center of mass velocity of all the particles together, and there are two events that you will do in the collision step. Once we will have a single component MPC event, the collision event, and once you will have the all particle collision event, and that way you can actually tune the alphas, right? You can tune your H when you will do single component, when you will do all component. That way you will be able to simulate two types of particles with two different viscosities for that matter. Okay. Okay. Now, another important point that I wanted to talk to you about is, as you have seen, the streaming and collision step, in none of these steps we involved any potential between the particles, right, between the solvent particles. So actually what we are simulating is an ideal solvent. Okay, it's an ideal gas equation of state that we have, right? So that immediately tells me that if I want to have, if you want to invoke the phenomena of, let's say, phase separation, phase transition, those are the phenomena that I cannot simulate in the present form of MPC. Correct? Because there is no potentials involved, right? Therefore, all the particles are, what they are doing is just colliding with each other and changing this thing, directionality in some way, but which is random again, stochastic again. So there is no mechanism for to bring the non-idealness or sort of separation between the particles, right? So if I want to invoke such experiments or invoke such phenomena, whatever we have discussed so far is not sufficient, right? So therefore, that means what? I need to invoke some mechanism, some method to bring in the non-ideal characteristics. Non-ideal characteristics means the particle will be able to see each other, okay, through some not real potential that way, okay, but particle will be able to distinguish itself from the other type of particles for that matter. And then I will be able to bring in this kind of phenomena which I was not able to bring in so far. Okay, right? And that actually, this is something which is a very recent work from our group, where we had, and actually there are some more work in this direction which has been done to incorporate non-idealness in the system and to bring in the phase separations and all that. So what we do in this case is, instead of having one cell, so you still have that box, okay? Now, instead of having one cell, we make a supercell of two cells, okay? And then all these supercells, how you will choose, okay, will bring in some directionality, some direction, For example, this sigma 1 is x direction, sigma 2 is y direction, sigma 3 is the z direction, and this is your xy plane, and so on and so forth. So there are 13 possible choices of direction for selecting a supercell. So I take supercell means two cells which are close to each other, right? And how you will choose these supercells will have 13 possibilities in a 3D system. Okay, x, y, z, x, y, x plus y, x minus y, so on and so forth, right? And out of these, right, phase diagonal in the xy, body diagonal, all these 13 possibilities, there are 13 possibilities only, okay, which one can choose from to make a supercell. Okay, now once we have made a supercell, we have to modify the collision rules, okay, such that if I have two types of particle A and B, they should be able to see each other as different type of particle and should move away from each other if they are trying to phase separate, right? And if they are not trying to phase separate, that's okay. But since our motivation here was to bring in the phase separation, okay, we had this kind of 13 pairs, 13 directions, okay. We calculated the average velocity, the center of mass velocity of A particle in one cell, B particle in the second cell, calculated the relative velocity of A with B, which is coming from, if they are coming in the same direction as the chosen direction, then they will have some collision with a probability, okay, and change the velocity accordingly post collision. I'm going a bit fast, I know, but I just want to give you an essence of what is being done here, okay. So you have these now two cells. You choose the A particles in one, B in the other, or vice versa, whatever. Okay. Now, if they have to phase separate, if the particles will have to interact and then phase separate, then they have to collide. They have to come towards each other in the same direction as I have chosen the direction, and then they have to collide and change their velocity according to some probability. Okay, and that is what we do in this case, and what we see is a beautiful phase separation, okay, by tuning that, which was not possible in the original form of MPCD. And you can see that this phase separation depends on two things: the temperature. If the temperature is very high, of course, the phase separation will not happen. On top of this AB collision, the AA and BB collision, single component collision, is as before within each cell. Right, so if the temperature is very large, we know the phase separation will not happen, and that is what we see. And also there's another system parameter, alpha. Sorry, this is not the same alpha as the rotation. This is a slightly different alpha. I'm sorry for this confusion. That depends on this system parameter, which basically brings is the probability of collision between the different types of particle. And you can see that by tuning this temperature and this collision parameter, you can see a very beautiful phase separation in the system. Okay, so this is in addition to what was there in the actual MPC simulations. How much time do I have for this talk? Okay, so what I'll do is I will quickly start how to do the complex structures, and then we'll break, and then we'll assemble again after.
Hello. Yeah, so what was the need to construct this supercell? If you wanted, you would have made this phase separation possible within a single cell also.
I would love to do that thing. Give me a solution. Why supercell? This is what we thought. Okay, this is what research is. This is what we could think of. If there are some better solutions, we can always go for that. What we thought is, everything has to collide with everything, right? So AA, same type of particle, has to collide again, right? BB also have to collide, and AB also has to collide. Now within the same cell, if I do the same type of collision, okay, which is randomizing of velocity, that will not bring in any phase separation. That is just going to randomize the velocity. That is just going to bring in the thermal fluctuations and other stuffs which we talked about. But how the A and B have to distinguish with each other is something which I could not think of. And therefore, and not only me, there were previous work also which had a similar strategy. Okay, but then if I choose two cells and I take A of this and B of this, right, and then they are trying to come to collide with each other, then I reverse the velocity or change the velocity such that they can phase separate, is something that we could think of in this case. Within the same cell, we could not think of how to do it. But if you have something in mind, we can discuss. Okay, so maybe in next 10 minutes, what we are going to do is we are going to see what else we can do. Okay, so what have we done so far? So far, we have just drank water, right? We just talked about solvent. But if it is lunchtime, this water is not enough, right? We need some noodles, pasta, something in that water, right? So that is what the next step should be, right? That we have to bring in this something more than water, which is the reality, which is what we need all the time, and try to find out how we are going to do it in this ambit of MPC. Okay? So one thing which is very clear is just having MPC is not sufficient. MPC is a method which will bring in solvent for you, right? And you can do whatever you want with the solvent, even the binary phase separation and all that, whatever I talked about is only with the solvent. But if I want to bring in more complex structures, if I want to bring in colloid, if I want to bring in polymers, right? I need to go for a hybrid model. I need to go something more than something MPC plus something, okay? And that plus something, where do we bring in is the question, okay? Now, in any of the simulations, there are 3 types of interactions which are there, right? Solvent-solvent, solute-solute, solvent-solute, right? So that plus, where will that plus will come is the question, right? So we now have thoroughly understood MPC and we know that is for solvent-solvent, okay? Now solute-solute, let's say if I have colloid, if I have polymer, or if I have membrane, right? There are models which are there for solute-solute also. MD is one type, right, which is there for solute-solute. If I have 2 colloidal particles, they will interact with each other through some potential, and I will evolve that through molecular dynamics. That's known, right? If I have membrane, then these triangulated surface membranes, those specific models are already there, right? So solute-solute is something that I can bring in through any of these. Let's say MD, okay? What about solvent-solute? Here, there are multiple options. Okay, I can bring in this interaction of solute-solute either through MPC coupling or MD coupling, right? Or any further coupling that one can think of here or anywhere else. Okay, for this particular talk, I will be just concentrating on these 2 types of coupling. And we work on MD coupling for solute-solute. Solvent-solvent MPC always. That has reduced the maximum amount of effort that will go in computation because we have millions of solvent, right? And I'll always do MPC for solvent-solvent. Now solute-solute, no other choice than do MD or triangulated or whatever is there. But solute-solvent is where I have the choice. Okay, and both the choices will have its own pluses and minuses. For example, let's say let's try to understand what do we do in MPC coupling. Okay, how do I couple a solute with solvent through MPC coupling? Now, what do we mean by coupling here? Coupling here would mean how the solute is going to interact with the solvent, correct? And when I say that when coupling of solute and solvent is through MPC, that means my solute, which is this big colloidal particle, is also an MPC particle, okay? That is what I mean by MPC coupling, right? So I have now 2 time steps, small dt and a capital H. Capital H, sorry, the dt and H. H is the collision one that we know of, right? That we do the collisions for the solvent-solvent. But this dt is for the MD. Let's say I want to do MD between the colloids, right? So I'll have a time scale for that molecular dynamics. So dt is something which is the time step for the molecular dynamics for the solute-solute interaction, right? So I'll do molecular dynamics, molecular dynamics, molecular dynamics, molecular dynamics, and then do a collision, right? And in this collision step, the interaction between solvent-solvent will come, and also the interaction between the solute-solvent will come. What does it mean? It means that now solvent, this big solute is nothing but a solvent particle in that particular box. Okay, so this one extra is added into the center of mass velocity and everything remains the same. right? That is weird. You would say that this is weird because you are assuming the solute particle, the big solute particle, to be a point particle. Actually, it is not a point particle when it comes to solute-solute collision interaction, because there I have the regular MD. But when it comes to solute solvent, I'm considering that to be a point particle. That means I am allowing the solvent to cause to the solute. Is it a valid assumption? Is it a valid coupling? Right? That's the question that will come to our mind immediately, right? And to show you that this is a very reasonable coupling, this is a work by Gomper's group where what they have is they have this polymer, okay, where the solute-solute interaction or between the monomers you have this potential, okay? So you evolve the solute polymer monomers with that small dt with this kind of potential, but at the collision step, when it comes to solvent-solvent and solute-solvent interaction, you just do a regular MPC that we have been doing, okay? And then calculate the center of mass diffusion and radius of gyration of the system of this polymer. And from the analytical theory, we know that for Rao's model, D goes as Rg to the power minus 2. For a Zim model, it goes Rg to the power minus 1. This is a model which has inbuilt hydrodynamics into it, right? Therefore, it should be a Zim model. The prediction should, if my MPC coupling is correct, my scaling of D and Rg should be Zim dynamics. Agreed? Everyone agrees to that? Because I have the inbuilt hydrodynamics into the system. I have the solvent into the system. And you can see the D actually goes as Rg to the power minus 1 in this case, right? So even if this coupling of solute solvent seems very naive, but it is able to give you the correct dynamics, which is what is predicted by theory.
Does this scheme work? Because essentially the net force on basically the large particle is random. So essentially we're simulating a Brownian dynamic.
Yes, yes, that's because of that. But many cases it may not work, okay? So MPC coupling is one way of doing things. And then the other one is MD coupling. Maybe we can take a break now and then come back to MD coupling in the next class. Yeah, okay, if you have any questions so far, please feel free. Otherwise, anyway, we'll have time.
So maybe we can break for tea. If you have any questions, you can ask Professor Thakur during the break. Also, I mean, she will be continuing the lecture after the break. Okay, so let's go for tea.
Mhm. Shall we continue? Okay. So yeah, so now onwards, I will go more on the research that we do. Okay, I hope I have made the point of MPC clear to all of you. And if there are more questions, we can take it during the discussion session. Now onwards, my job would be to give you a flavor of what we are doing in the lab using MPC. And then I will also go later on without MPC work also, which we do, and then give you the advantages, disadvantages, and so on. Okay, so I left with two types of coupling, right? When we want to bring in pasta noodles, sauce, and all that in the system, okay, other than solvent. So this is the coupling that we work on, which is the MD coupling. Here you can see that the solute-solvent interaction is no more through MPC, it's through the MD. That means the solvent now recognizes the solute, okay, and they will be able to do what the solvent would like to do. It is not unlike the MPC case where the solvent can pass through, does not see the solute particle, and all that is not going to happen anymore. Okay. Quickly about what is in this in this MD coupling. The difference is now this part where the solute and solvent also interact in this time step dt, okay, and the MD potential between the solute and solvent may vary depending on the problem under consideration. You can choose different types of potentials between the solute and solvent, okay. Solute potential, we saw, let's say for the polymer case, what is the typical type of potential people do. Solvent is also very typical potentials which people use, and it's still with those kind of typical potentials also very nice effects which we see here. Okay, so I'll come back to these genus colloid that I started with in the beginning. Okay, what happens experimentally in these genus colloids? These particles, which are few micron particles, are put in these solvent, and there is reaction that happens only on one side of this genus particle, right? And that reaction seems to lead to the propulsion of this active particle, right? And that is called phoresis. This is called diffusophoresis, which brings in the motion of these kind of particles. Now we simulate that in our framework, okay, where we have now the solvent. Now we take this genus particle, now we model this genus particle as two spheres connected by each other. It's called dimer, okay. One of them we call as catalytic, the other one we call as non-catalytic, okay. Now the catalytic one is different from non-catalytic. So catalytic one you can think of as the platinum side of this genus, right? And there is some reaction that happens on the catalytic side, like the genus. Non-catalytic side, there is no reaction that happens on that, okay. So what we do is, to start with, we make these genus. How do we make these genus particles? We have two beads which are connected either by rigid rod or very stiff ring. Those are the details which we should not get into right now. So they are connected by each other and they are immersed in a A-type solvent, okay, which is like hydrogen peroxide, right? Now, on the catalytic side, this A are now my MPC solvents, okay? On the catalytic side, the A goes to B. B is a different type of solvent, right? In the actual reaction, H2O2 goes to H2O plus oxygen, right? Here, we are not bringing in the additional particle creation. What we are saying is particle changes its type. Now, when we say changes its type, that means the particle now will have a different interactions, okay? And what we will show, as I'll show you today, is this kind of change in type of particle is sufficient to bring in the effect that we see in the experiment. Okay? Yeah. Oh, okay. Okay. So this hydrogen peroxide fuel going to product is what we simulate here by changing the A, which is fuel in our simulation, to product, which is B in our simulation.
Ma'am, here the genus particle is not a single particle, is it?
It's not a single particle. You can make it also a single particle. That's not very difficult. Okay. But it's a dimer right now, two spheres connected to each other.
Via?
Right? Because it's easy to do it in simulation.
Like,
that's all.
They're connecting via what? Like what are you
Either you put a rigid rod or a stiff ring or whatever, but they are connected.
Okay, not a spring.
A spring also, stiff spring is also possible. We don't want too much of fluctuations because genus is a rigid this thing, right? So I wanted to, initially we had put a rigid rod here, okay? And we saw that we can change it with a stiff string or spring also, but if your spring is very flexible, things change a bit, velocity change a bit and all that. But they are connected to each other. But right, you can also make one sphere to half also. This is computationally easy, and therefore one started with this kind of modeling. Okay, but the bottom line, yeah.
So when you convert A to a B type particle, there is usually some kind of a reaction rate associated with it.
There is a reaction rate associated with this.
So how do you incorporate that time scale into your simulation?
Okay, so that results I will not show you right now. Here, right now, we are saying that the reaction rate can be associated in this case by the probability of conversion of A to B. And right now we are saying is probability is 1. So every particle which is going to come in certain cutoff of C is going to get converted to B. But you can control, we have done that in some other work, we have controlled this A to B conversion by the probability of conversion of A to B. Okay? So now you can see the advantage of this simulation method. This kind of particle-based reaction, which we are able to do, was not possible in Langevin, is not possible in BD, is not possible in any other hydrodynamic solutions that we have talked about. It's possible here, right? Now, what is the outcome of that? So now, whenever A goes in contact with C, it converts to B. That automatically tells us that there is a gradient of B which is going to set up in the system. Okay? Okay. So this is the actual simulation snapshot. That was just a cartoon. This red is my catalytic particle. This is my non-catalytic particle. Blue is the B particle. Gray is the A particle. What you see is you have now a gradient of product B particle which is set up, right? And now this kind of gradient of B particle, you can see more blue here. Now gradient is set up around what? Gradient is set up around the N sphere. Around the C sphere, it's all symmetric, right? But around the N sphere, if you see, there are more B at this side and less B at this side, right? And because of that, what you see is a very directed motion of these kind of genus particle. It goes for a long distance, right? Something like superdiffusively or ballistically, in fact, before reorienting. So you can now calculate the mean square displacement, right, as a function of time and see what kind of self-propelled particle it is. And it seems it depends on the size of the motor. Okay, Rm in this case, which is the size of this non-catalytic guy. Non-catalytic guy is also important because that is where the gradient has set in, right? Depending on the size, if the size is very small, you will always see the diffusive motion of this kind of particle. You will not see this kind of directed motion. But if size is substantially large, okay, you see a ballistic followed by a diffusive. Why small size will not give you ballistic motion? Because you have thermal fluctuations, right? You are at a finite temperature, therefore it will just randomize the motion. Whereas if you tune the motor size, you can see a very nice ballistic motion in this case. Okay, now the question is, why does it move? It moves because of something called self-diffusophoresis. Phoresis, you all know, is a phenomena of movement of any particle, colloidal particle or any particle in presence of a gradient, right? If it is thermal temperature gradient, it's called thermophoresis. If I put a colloidal particle in a temperature gradient, it will move. That's thermophoresis. If I put an electrical metal colloidal particle in electric field gradient, it will move. That's called electrophoresis. if in this particular case, a colloidal particle is put in a concentration gradient of this product, right? And it moves. Why does it move? It moves because, okay, it moves because you have this kind of asymmetry of the product particle here. In this case, I'm saying product, but in general, if I want to see concentration of the solvent around this solute. Now, what happens because of that? Oh, there is this bottom is getting cut. Okay. If you put the cursor somewhere else, I think it will go. Yeah, it goes. Okay. Okay. So now what happens? Think about this. Okay. One side of the solute. So within the cutoff region, so whenever you have a solute particle on a colloidal particle, it is going to interact. Okay. Now interaction of this, okay, will go to a certain distance, and beyond that, the solvent will take this kind of constant velocity, bulk velocity, and we call that to be a slip velocity. From the surface to the bulk velocity, what is the slip that you get the solvent? Okay. Now forget about the slip velocity right now. What happens? Why this moves is because you have a force, you have a gradient of the solute. So that means the force that the solvent is going to give to this colloid at the front and at the back is going to be different, right? And that difference in force will give a direction of motion to the colloidal particle, right? And how much it is going to move will depend on this kind of slip velocity, which in turn depends on the gradient, okay, and the interaction strength. Lambda is the interaction strength of solvent with the solute. Yes.
Think about this problem from a very naive point of view. If I have concentration gradient, diffusion would like to make the concentration very similar. So I expect that there will be some pressure from the high concentration gradient to low concentration gradient. So I expect the force to be from the high concentration to the low concentration region, right? So with that intuition, I would expect the particle to move down the concentration gradient, but it seems that it is going up the concentration gradient. So why is this happening?
So down or up, actually, in this particular case, what you are just thinking is the diffusion of the solvent, right? There is something which is happening on the surface, right? That is what is happening is the solute here, okay, is interacting and giving a force, right? And solute, so if there is no gradient, if it's all symmetric, the force that the solute is going to give is going to be symmetric and that will cancel out. But now let's say you are getting more force here and less force here, then it will have direction of motion like that, right? But what kind of potential, the interaction that you have between solvent and solute is unknown. Okay, and that decides the direction of motion. Okay, in some case, you will see it can move up the gradient, it can move down the gradient, depending on whether it likes the solvent or it dislikes the solvent. Chemotaxis, right, for that matter, right? Okay, so how do you calculate the velocities? By calculating this slip velocity of the solvent, which in turn depends on the gradient, strength of the gradient, and the interaction between the solvent and the solute. Okay, and actually we can do analytical calculations and get determine the VZ for this particular our dimer case, okay, and get it from the simulation, and we can see that there is a good match first of all, and secondly, this is the VZ versus time. You can see as you increase the size of the non-catalytic particle, the surface area for the interaction increases, right? And therefore you get more and more velocity. Okay, so it's called self-diffusophoresis. Why? Because it's a diffusophoresis, but the gradient that is required to do this diffusophoresis is not externally given, it's internally coming to the colloid, and that's why it's called self-diffusophoresis. Okay, and the way we model, I hope that is very clear, how we model that. The way we model that in our simulation is by doing this kind of explicit solvent based simulations. Okay, and actually now you can tune the parameters. You can say, okay, by changing this n, how the size of the n, what is going to happen, velocities, directionalities, random rotations. You can now go to the experiments and then match the velocities. You can do all sorts of stuff that you would like to do in this case. Okay. Now collective motion, which is what we all strive for, is that this behavior shows a collective, this whole thing shows a collective motion. In fact, we do see that this kind of very nice collective motion is observed in our simulations also. Now, here I have the advantage, okay, over other methods maybe, because now I have this explicit solvents, I can actually see whether this effect is coming because of the gradient of one produced by the, it can happen that this guy which is producing the gradient, this is also producing a gradient. This can see this guy through this chemical gradient. Also, this can see, this guy can see the other guy through the hydrodynamic flows. I have now the solvent inbuilt into it. Okay, I can now see the interplay between the gradient, the chemistry, the chemical gradient and the hydrodynamic flows. Okay, and how do I do that? What we can do here in this particular case, I did not put the results, but I can tell you. This is the advantage of MPC solution, that despite of presence of solvent, you can actually switch off the hydrodynamics here. Okay, switching off hydrodynamics means what? You have to just decorrelate. You had certain flows, right? For example, you had this guy moving in this direction, let's say, and had created a flow, right, in the simulation. I can now go back to the boxes which had produced these flows. I can decorrelate the flows here, right? Why? How do I do that? I can do that by picking up the velocity, randomly changing the velocities of the particles in the solvent, right, in each of these boxes. So the hydrodynamic flow which was set up like that can be destroyed even in the presence of solvent, right? And what is the advantage of doing that? Is advantage in this case would be chemical gradient will be intact, right? But I have now switched off the hydrodynamic gradient, and I'll be able to see what is the effect of chemical gradient and what is the effect of hydrodynamic flows, which is more relevant, which is less relevant, and so on and so forth. Those are the questions that we can ask now in this case. Okay, and it seems in this particular case, a small number of particles, we did see that the chemical gradient plays a very important role. Okay, this guy, even if I switch off the hydrodynamics, okay, the whole thing becomes slow. Okay, but the collective, the particles coming together still happens. Why? Because this guy is able to see this guy through this gradient. Okay, hydrodynamics speeds up the whole thing. Okay, but the collection, the swarming still happens in this case. Okay, which is which I feel is an advantage in this particular model. Okay, the second thing that we did, this is a very recent work, maybe a couple of years back, is what we did is there are now recent experiments where people are trying to see the effect of viscoelastic fluid, okay, instead of Newtonian fluid. Yeah.
Ma'am, like what earlier has been done, is it like people consider some kind of concentration gradient and they move the particles? But like, I didn't understand exactly how your work is different from what has been done earlier.
Okay, so the diffusophoresis is a very old phenomenon. You can see that. Okay, where it is shown that if you put an external gradient, put the particle, and then it will move because of the presence of the gradient. Okay, now this Janus particle work, which is sort of much recent than the diffusiophoresis work, came in 2005, where people exactly showed in the experiment that this moves, okay, and started with bimetallic rods. So it was not clear what kind of, so everybody understood that there is some sort of phoresis which is happening. Okay, you have asymmetry either in the electric field because these are metallic particles which is undergoing this kind of reaction, oxidization, reduction, there'll be H plus, and then that will create a electric field. So people propose at that point of time, it's the electrophoresis which happens. Okay. Later on, this experiment was done on a dielectric, on a silica particle, which is not a metallic. Still, same thing was seen. Okay. So what was the question? So this work that I had shown is a very old work again, about 10 years back from our group. In this work, what we had established is, look, it is a diffusiophoresis. You don't need any external, any electric field or anything of that sort to explain this motion of silica particle. It is a diffusiophoresis work. And then the advantage, in this particular work, the advantage to show that this method, okay, which was a new method at that point of time, works really well to explain this. Okay. And then this was another work which was shown to, which was done to show the collective motion of these kind of synthetic particles. Okay. And this work, the advantage was to show the effect of each of these gradient, each of these forces, the chemical gradient and hydrodynamic flow. Okay. Which is impossible to detect in the experiment. In experiment, this is not possible for you to tell this swarming or this collective motion in case of these kind of genus particle is happening because of them interacting through the gradient or because of hydrodynamic flows, or both of them are there, one is dominating over the other, or what is the role of these two things. Okay. And in this work, we can actually show that your hydrodynamic flows, what it does, it speeds up the stuff, the collective motion. But the collections, things trying to come together and trying to move together will still be happening because that is happening through the gradient which is present in the system. Okay, so what you can do now, okay, there is no result to show you here for that matter. In this work, which I am just showing you that this thing particles are coming together and swarming. But what you can do is you can calculate the center of mass velocity of a swarm. Okay, and you can switch off the hydrodynamics the way I said. Okay, have the solvent, but switch off the correlation between the solvent. That means destroying the flow. Okay, and then you calculate the center of mass velocity again. Okay, and then you will be able to see that this center of mass velocity is switched.
Is basically only due to the chemical gradient.
In this movie, both are present.
Both are present.
In this movie, both are present.
Okay.
Okay. But the advantage here in this simulation method is I can switch off at least hydrodynamics very easily. Okay. If I switch off the chemical gradient, of course,
no flocking.
It will not happen to this kind of this extent.
Okay.
Okay.
So hydrodynamics is just like helping me basically to increase the velocity of the
velocity of the whole thing.
Okay.
So if you switch off the chemical gradient and keep only the hydrodynamic gradient, so don't we see the swarming like it might not be this problem?
In this particular case, you then need to put in some method for them to move. You have to put some velocity, right? You have to put some self-propulsion, okay? Which will not happen in this case if I switch off the chemical reaction. Okay, is it clear? It can, okay. That's something which is not important as far as you are trying to look at the movement, okay? That will decide the velocity of the whole thing, okay, of this assembly, but you can also do with the symmetric particles.
Ma'am, since this flow is helping this particle to move, so may I see how the flow profile will look like?
Okay, I will be able to, I'm not sure whether I have it today, but I will show you. Okay, during the discussion time or sometime I'll try to show you. Or maybe I'll have one slide where the flow profile I can show you. Okay. So the next thing that we tried to do is so the algorithm so far doesn't allow me to go to a solvent which is viscoelastic. Okay, the solvent so far is a Newtonian solvent. Okay, but if I want to see the motion of this kind of object in a viscoelastic solvent, I need to modify my method, my MPC method. Okay, and that we could do here because we had these point particles present in the system. We connected the point particles through this harmonic potential. Okay, and the strength of this kappa, actually the two limits actually it brings me back my Newtonian fluid. If I put kappa equal to 0, that's like Newtonian particle, Newtonian MPC. But if I put a finite kappa, that will have the spring. So I will have the solvent which will have the viscoelasticity. Correct? Right? And the other limit, which is kappa infinity, that's again point particles. Right? That's again a Newtonian fluid with different viscosities because your density would change. Okay? Huh?
When kappa is infinity, you essentially have a dumbbell-shaped particle, right? Because they are connected by a spring.
Yeah, but you don't have an equilibrium length here.
Okay.
Equilibrium length is 0.
Okay.
So it will be a point particle.
Okay.
With reduced density now.
Got it.
Okay. So my transport properties will change. Okay. But what we do actually is compare the finite kappa with a non-zero kappa, which is like comparing the Newtonian with viscoelastic. There are a couple of technical stuff which I am leaving out here, which is required for the viscosity matching of the two solvents and all that, but we have done those things here. But the bottom line is, the moment when you have the Newtonian fluid, okay, the Vz versus Pe, this Pe is something which is the activity, okay, active force, okay, that goes linearly, velocity goes linearly with the force. But the moment you have the viscoelasticity in the system, that goes more than 1. Okay, that means viscoelasticity helps in the motion of these active particles. Okay, now the question is why? That why question is something again we can address because we have this kind of model where we have the microstructures present, we have the solvent present in the system, and then that means we can actually see what is happening around the system, around these dumbbell particles or these dimer particles, what makes them move faster. Okay, and what we calculated is this orientation, this phi, the theta, average theta is the orientation of each of these dumbbells, solvent dumbbells around these dimers, and you can see that as you increase the Peclet, that means the activity, the faster this guy moves, the dimer moves, right? The active particle moves, it tries to align these microstructures, okay, along it, and that helps the particle, the active particle moves faster, right? So the alignment is something of these microstructure, of these fluid structure, is something that we can now see in the simulations. And the effect of that is something that we can see, that enhancement of the velocity which is seen in this particular case. Okay, right? So that's the advantage of these simulation methods. Okay, any questions so far? Otherwise, I'll go to the polymers now.
Hello, ma'am. Hello.
Oh, I'm sorry. Yeah.
Yeah, I'm an online participant. So I just want to understand one thing, that how do you quantify this activity, like when you are modeling this system? So how are you introducing this activity in that model?
In which one? Can you be specific for the viscoelastic you're talking about or the previous one that you're talking about? This one?
No, for the viscoelastic I'm talking.
The viscoelastic one is more simpler. Okay, here we have ignored the origin of activity. For example, in this one, the activity where I'm talking about the Janus particle, a chemically active Janus particle, here the activity was introduced by having the chemical reaction on the sphere, dimer sphere. Okay, but when I go to viscoelastic work, what we said is, okay, origin of this activity is not very important to us. Because what we wanted to see is what is happening because of the solvent. The nature of the solvent is changed. Therefore, what we did is we just put an FA in that particular case. We had just put in force in this particular case. Origin of that force was not important, but it can come from the chemical activity also. Is that does that answer your question?
Yeah. Okay. Thank you.
You had something? Okay, let's move forward then. Okay. Okay, so with this, I think I come to the last part of the talk, which is what I want to concentrate on in terms of the research. We would like to, very recently, we have got interested in these synthetic active particles, and one of them which I showed you in the beginning, where you had these chains of Janus particle, which showed this kind of ring structures, linear structures, which show cilia-like beating and so on and so forth. And there are other synthetic active polymers which are now there in the literature. And there are different types of synthetic active polymers which are there in the literature. For example, in this particular case, this is a magnetic chain. The chain itself is not active, but it becomes active because it is immersed in a bacterial bath. Okay. Now, what happens is one can see that by increasing the activity, this is something which is a measure of displacement, mean square displacement. You can see that this exponent, it becomes more and more active. It moves more and more. So by having the activity in the system, you can make the particle move faster and faster. But in this case, remember, the chain is not active. What is active is the medium.
So
okay?
How exactly are you controlling the activity? It's
by in this particular case, this is the bacterial concentration. That
so the higher the concentration, the more active it is.
More active it is. Okay. Now this is another model for these are all from different groups. This is another model, experimental model for active polymer. Here the polymer is made active. Okay. And how they did it? They did something called ice templating. So they had these colloidal particle which had the platinum particle on it. Okay, you can see these black spots which are platinum particles, and then did some sort of a ice templating for connecting these colloidal particle, and they got this kind of chains of these colloidal particles. So the chain itself is now active. They immersed it into hydrogen peroxide, and then they show the enhancement of diffusion. It is again not super diffusive chains or anything, but what they showed that enhancement of the diffusion constant as you increase the activity of the system, and also the size dependence and so on and so forth. Okay, so in this kind of work, it is the chain that becomes active, right? There are other examples of active polymer. For example, the worm that we see, right? That's also a active polymer. Okay. Now, how and that polymer, this is also very interesting polymer. This work, it's very not very old work, it's recent work only. What they had done is they had two worms of different activity, okay, and they did a rheology in the system. And what you can see by changing the activity, okay, the shear thinning that they see in the system is reduced by activity, right? So if you have more activity, the shear thinning is something which is reduced in the system. Okay, that is because of the alignment. Now, just to tell you the lighter node, how they decrease the activity of this worm is by putting that worm in an alcohol solution. Okay, so by making this worm drunk, actually they are reducing the activity of the system. And what they show is by reducing this activity, the shear thinning is reduced. Sorry, shear thinning is increased. Now, why that happens? The way they explain that is when they are all active, they are all trying to align in the shear direction very rapidly, and therefore shear thinning happens, whereas it doesn't happen in this reduced activity case. Okay. The other example of active polymer, which is where we have a long length, these kind of polymeric object, and activities playing important role is chromatin, right, which is where a lot of active processes are involved during the transcription and other processes during the in the chromatin that leads to different sites on the chromatin. It's called heterochromatin, which is called euchromatin, right? And then there's a very recent work here which says that correlated active force can mediate in the effective attraction between the polymer segment, therefore formation of the compartment. So if you have a long chromatin molecule, what they showed is if you have correlated active force at certain part of the chromatin, that correlated forces will lead to effective attraction, and that will lead to globule formations and in different compartments of the active. So these are something these are the work that has been going on in the literature for the active polymers. And to understand these work, of course, there are a lot of simulations which are there, and we are also working towards that direction. The different simulation work which I will present here before going to our work. There are different types, as I said. One type is where different types of forces. There are two main type of forces which are present when we talk about the active polymer, two different class of forces. One class of forces is called Brownian forces, which is where the model is called active Brownian polymer. So what happens is the polymer, either the polymer is active or the medium is active, such that each of these beads on the polymer, right, will have some sort of a random forcing on it. Okay, so there are these Brownian random forcing which is there on the backbone of the polymer. It could be because of the bead itself being active, like the second case, the ice templating case, where you had the platinum particle coated on the gold, or the magnetic chain immersed in a bacterial solution, where the bacteria is giving these random kicks to each of these polymers, right? And this class of active polymers are called ABPOs. And what is one unique feature that is shown in both these types, whether it is polymer being the monomers being active or the solvent being active, is if you plot the RG or RE versus the Peclet, the activity, okay, what is shown is that the chain to end-to-end distance exhibit a non-monotonicity as a function of activity. That means what? As you increase the activity, the end-to-end distance first decreases and then it increases. That means by changing the activity, first the chain tries to collapse and then it swells. Okay, and both these papers shows that. And the reason that you can think of is when the activity, let's talk about this case. Okay, let's talk about this case where bacteria is coming and hitting the polymers. What happens is bacteria activity is small, means bacteria is moving slowly. Then once it comes and hits the polymers at different ends, it makes this kind of curly structures. It makes these kind of hairpin structures. And if you have multiple such hairpin structures on the polymer, the end-to-end distance would reduce. That means at this activity, the polymer is trying to collapse. Okay. However, when the activity of the polymer of the bacteria is pretty high, what it does is after hitting the polymer, it will slide along the polymer. Okay, and that therefore stretching the polymer, right? So and the same origin is same thing happens in this particular case also. And in both of these cases, one sees a non-monotonic behavior of the RE versus Peclet, right? The other model of the active filament, which is there in the literature, is where they introduce some sort of a Wyschik activity on the monomers. Okay, so what they say in this particular case is a monomer will be active, will have certain direction of motion, but the direction of its motion will depend on its neighbors. Okay, and in such cases, what they showed, if you look at this RG versus T plot, or so RG versus T plot, let's say FA0. Okay, that is no activity, right? It's a passive polymer. Your RG falls like that. Okay, as you increase activity 0.51, so 0 to 0.5, there's a sudden change in RE or RG. Okay, so that means it collapses faster, right? But the moment you increase Fa, beyond that, the collapse becomes slower and slower. That's again like the previous case. There is a non-monotonic dependence of the Rg or Re with the activity. Okay. Now, when you don't have any activity on the system, it's a passive case. It goes from a stretch state to a collapse state. By the way, in this case, it goes to a collapse state because there is a short range attraction between the monomer, right? So the preferred state is a collapse state, even in the passive case. So it goes to a collapse state. But the moment you switch on the activity for smaller activity, it goes to a collapse state much faster. So activity helps in the collapse of the polymer, okay, in this model for small values. However, the moment you have very large activity, what happens? What is this model? This model is like a Vishik model, right, where things are collapsing and trying to orient its velocity in a certain direction, right? So if the activity is very, very, very large, this kind of two beads will form, okay, and these two beads will try to move in their own direction, right? So the chances of them coming close to each other and going to a complete collapse state will be very less. Therefore, it will take much more longer time as compared to the smaller activity. Smaller activity, again, the collapse, small fragments will come together and make these globular, these pearl-like structures, right? But these pearl-like structures are all again randomly moving, right? Because activity is small, so they can come close to each other much faster, and that reduces the collapse time. Okay, but if the activity is very large, right, because their motions are completely in a different direction, the time taken for them to come together will be very large, right? So there is, even in this kind of activity, there is a non-monotonic behavior of coarsening time, okay, with activity, right? So this is a different type, different model for the active polymer, which shows this kind of non-monotonic behavior. Right, the second class, yeah.
Maybe a naive question, but like when we have activity in the filament, so why it is collapsing?
Okay, see, even in this particular model, okay, let's talk about model by model, because I am trying to give you a gist of what is there in the literature right now. So in this case, in the passive case also, it goes to a collapse state. The question is why, right? That is because there is a short range van der Waals attraction between them. So ultimately, it is trying to come to a collapse. So any monomer, when it will come under certain range, okay, they will collapse, right? So even in passive case that happens. For a small activity, this kind of random motion, this motion increases, and therefore the probability of them coming close to each other increases, because still these small pearl-like structures are moving, right, in certain directions which are random. Random in the sense they are taking directions from their neighbors, right? So the probability of them coming close to each other will be more than the passive case. Therefore, time for coarsening, time for collapse will be shorter. However, when you have a large activity, these guys, let's say, have formed, but they will, up to a certain time, they will come close to each other and then they will collapse. You can see 50, 50, 50, there's not much of a difference. In fact, there is more collapse here. But when it comes to, let's say, this structure, this time, by that time, it has gone to this two blob case. But these two blobs are not coming close to each other because their velocities are very large now. Okay, and they're all moving in their own direction. Okay, so they have got a clump which is trying to move in their own directions, for example, this direction or that direction. Therefore, the probability for them to come close to be able to make a globule becomes lower. Does that answer your question?
Speaking on that, so you said that two blob case, so they try to go in their own direction. The probability of coming together is very low, but eventually when they do, so does this cluster have like one direction or like the
once it will make a globular structure, it will have one direction. Okay, because it will be within this Vishik cutoff and all that, it will have one direction. Okay. Okay, so that is this. These are the two different types of activity. The third one, which we are also interested in, is called polar activity. So what you have here is these polymers, okay, and then there is this forcing on each of them, which is along a direction on the backbone. Right now, you can think of, if you really want to think of in a biopolymer point of view, if you have these biopolymers and if you have motors working on the biopolymers, the motors will not give a random force like the previous case. It is going to give a local force which is going to be on the backbone tangential to the monomer, right? So when I move, I give a tangential force. Similarly, when the motor is going to work on the filament, it is going to give you a tangential force, right? So this kind of forcing is very different from the forcings that we have seen before. And then in this kind of forcing, what was shown by an earlier group is this forces leads to a monotonic collapse of the polymer. The more you are going to change the Peclet number, the more it is going to go to a collapsed state very, very, very systematically. Okay. Now this is something where this was a case where people had done this forcing by just putting some numbers and all that. And what we wanted to do is we wanted to go to a more realistic picture, and we say, okay, what if I have a polymer which is a chemomechanically made polymer, like the chain that is made from the genus particle, where each particle is getting the force, the unit force along a particular direction by the chemical gradients, by the chemical reaction that is happening to it. Can I do that? Now the answer to me was very simple. Yes, we have these dimers. If I connect many of these dimers together, what I will have is a structure which is like the genus chains that we see before, right? And you wanted to see the velocity profile of single of one of them, and this is the kind of velocity profile that we see in the simulations. Okay, so if I put many of them, which is trying to have upward direction, a polar direction, right? So it's a polar forcing. If I connect more all of them, I will have an active polymer which is having the force local tangential force in each of them, right? Now I can tune the activity, right? I can tune the interaction between the solvent and the solute, and that way I can tune the velocities of each of the units, right? That means I can tune my active forces. Now the question was, what will happen if I tune my active forces? Now this is just the technical details where how we put in the interactions between the solvent, and this Peclet number is something that decides the strength of the activity that we tune by tuning the strength of force of A with the dimer. Okay, A and B with the dimer. So for the timing, you can just think of by changing the quality of the interaction of the solvent with the solute, I can change the activity PE. Okay, now what happens if I change the activity? Passive case, which we define in our model as PE1, not PE0. Usually passive case is PE0. Our definition of activity is such that PE becomes 1 for the passive case. If I have a passive polymer, okay, it will always be in an open state all the time. Okay, but the moment we have activity induced into this, it goes to a collapsed state, right? And this collapse, so there is a coil to globule transition which is observed in our active polymer. Now you can see this coil to globule transition very, very, very systematically. You see, this is the distribution of, or you can see here, okay, for that matter. Let's look at a large NM. NM64, NM is the size that decides the size of the polymer. For a larger polymer or for all sizes, what you see as you increase activity, the Rg reduces. That means it goes to a collapse state very, very systematically. There is no non-monotonicity here. Monotonically going to a collapse state as you are increasing the activity. So there is an emergence of compact globular state due to the chemical activity on the polymer. Now the question is, why this kind of local activity that you have brings a globular state, right? So you think about a rigid rod, right? If you have a rigid rod, if not completely rigid, let's say semi-flexible rod, if you keep applying a tangential force on the backbone, okay, what it will do? It will try to strengthen, right? It is not trying to collapse. It will try to swell. Intuitively, it looked to me at that point of time, maybe it will be more clear to you, that if I apply a polar forces, it will always stretch. Then the question is why it is going to a collapse stage when I am applying a polar forces, a tangential forces to the polymer. Okay, and it turned out that so this green is my polar forces, the tangential forces that is coming into picture here due to the presence of all these dimers, right? These tangential forces can be decomposed in the perpendicular component and a parallel component, parallel to the end-to-end vector. Okay, and one can see that whenever there is a change, there is a curvature, okay, in this system, which is bound to happen because you have flexible polymer, right? Flexible polymers will have many the curvatures, right, at multiple places. And the moment you have curvatures, these perpendicular forces component is going to change its sign. That means what? It is going to bring them closer and closer, right? That is like compactifying the polymer. The RE would reduce, right? And that is what we see in this particular case, right? We can now calculate the Flory exponent, which is a known quantity in the literature, right? And that Flory exponent goes as n to the power 0.6 for a passive system. It's a known thing in the polymer literature. So first thing that we try to see is are we able to reproduce what is there in the literature? In fact, we see a very nice 0.6 scaling, and as we increase the activity, the Flory exponents continuously decreases. Now, the decrease of the Flory exponent is an indication that you are going to a globular state, because in the literature it is shown that for a flexible polymer in an open state, you see a scaling of 0.6, but once it goes to a collapse state completely, okay, it will show you a scaling of 0.3. Okay, and that is the scaling that we are approaching as we are increasing the Peclet number or the activity of the system. Okay, one can actually, we have also went back and tried to correlate our results with the previous result, and we could see a very nice correlation between the previous result, though the origin of the forces were very different in those two cases. Okay, right. Now then we went ahead and talked about the dynamical behavior, what happens to the diffusion coefficient for that matter. If I have a passive polymer versus active polymer, you can see that the diffusion coefficient increases. How do we calculate the diffusion coefficient in these cases? You actually plot the mean square displacement. The mean square displacement for a passive case will be diffusive all the time. But for an active case, whether it's a polymer or a dimer, all of them at large length scale will show, large length scale is going to show you a diffusive regime. So one has to reach that diffusive regime and then get the slope of the MSD and then calculate the D from that. Okay, so activity not only amplifies the diffusivity of the polymer, which is intuitive also. The beautiful thing here was we could show that this D as a function of n shows a very nice Zim type of scaling in this particular case, even for the active case. Okay. The other dynamical behaviors like relaxation of the polymer, right? So we calculate the relaxation time as a function of Nm. Okay. The literature again shows me what is the scaling that I should observe. The scaling shows tau of r should go as n to the power 3 mu. Mu is the Flory exponent. Okay, we could see the same scaling for all the activity. Interestingly, the relaxation time of the polymer now reduces as you increase the activity. Okay, so that was about the ring polymer. I'll quickly go through that was about the linear polymer. Next, the question was what will happen if I'm going to change the topology from ring to linear.
Excuse me, ma'am.
Yeah, yeah.
Will it show super diffusive behavior?
The active polymer?
Yes, ma'am.
It does show a super diffusive behavior. Here you can see the scalings here. For the intermediate time, it will show a super diffusive behavior.
Okay, ma'am. Thanks.
Okay. Okay, so what will happen if I change the topology of the polymer from linear to ring? What I was showing you was linear. What will happen if I change it to ring? Okay. Again, this is like activity, which is like PE before, activity number. 1 corresponds to passive case. As I increase, it goes to a collapse state. Okay. Now, in this particular case, actually, I can reduce it from 1 also. Okay, because of my system and all that. And less than 1 will present a chemo-repulsion. Okay, let me just tell you one more thing, which I did not tell you before. Even for the linear case, maybe let me go back to the linear case, and I will repeat a couple of stuff here, sorry. Just to make things more clear. Okay, everyone are with me here, because this is important to understand. Okay, what I told you is each of these dimer individually is a self-propelled particle, right? On each of them, I will have a force which is local tangential, correct? But if I have multiple of them here, right, locally you will still have the tangential force, but the gradient which is produced by this, the fuel gradient which is produced by this, is a long range. It's going to diffuse for a long distance, right? Therefore, a dimer sitting here will also sense the gradient which is produced by the others, right? So there are two things which are there in this particular model, right? A local force, right, which is coming due to this this dimer present, the single dimer, and a long range interaction between the two dimers which are sitting through the chemical gradient, right? Hydrodynamic flow is anyway there. Through the chemical gradient, there is a long range attraction between the two of them also. Okay. So in this way, whatever I have shown you so far just tells you that, sorry, okay, maybe I should go there. And so this just tells you that the globalization happens. Okay, it doesn't tell you which is bringing, what is more important, whether it is the long range force or this long range force or this short local forces. That's not very clear to us so far. Okay, keep that in mind, because I'll come back to that after a few slides, right? There are two types of forces which are there in the system in this model or any chemically active polymer, even in experiments, right? Local as well as global, because the chemical gradients are not local. They will move to a large distance and will produce these long range forces. Okay. Okay. Now coming back to this long range forces. Now in principle, whether all of them will like the gradient and will try to come towards each other, or dislike the gradient, will try to go away from each other, will depend on the fuel that you have and the product that you have. Correct? So in principle, both are possible. In principle, it is possible that you can have them coming towards each other through this long range. Okay, they can try to go away from each other also through this long range. Okay, and that's what we name it as chemoattractant and chemorepulsion. Okay, and one can show that in case of chemoattractant, you will get a globular state, but in case of chemorepulsion, you will not get a globular state. Okay, again, there are a lot of open questions here. In this globular state, is it that only the local, the attraction which is important? Okay, or the local forces that you see is also important. I will come back to this point again. Okay, but keep in mind that this globular forces, globular state that you see here, So far, it is not clear to us that which is an important force which brings this globalization. But in the repulsive case, of course, it is going away from each other. Okay, and it's a swelling in that case. Okay, so again, we did the same type of the same type of analysis, and could show that even for the ring case, like the polymer case, we could show a very nice decrease in the Flory exponent for the chemoattractant, and increase in Flory exponent, which shows the openness of the ring as you decrease the type of the solvent, as you change the type of the solvent. Okay. Now, extent of collapse is something that was interesting to show, that depending on the size of the ring, okay, the question is, will all the ring show a collapse state or not? Okay, for the linear polymer, all the size of the linear polymer was showing us the collapse behavior. But in the ring structure, because there is this added topology constraint that comes into picture, the question was, will all the rings show a collapse state or it will not show a collapse state? Okay, and it turns out that when I have small n's, okay, small n's, the collapse is not there. The topology of the polymer is not allowing, because for a small ring, it's like a stiff structure, right? The topology has to be conserved, so it is not able to collapse further. So for a small size, the ring will not collapse. It is going to collapse only beyond a certain size of the polymer. Okay? Smaller rings, even in presence of large ring diffraction, has decreased ability to form the globule. That is because of the extent, that is because of the topology effect which is coming into. What will happen if I compare the ring and linear? Right? You can see that again, this is a small size ring. This is a large size polymer. If I have small polymer, right, the linear goes into a collapse state, the ring doesn't go to a collapse state. However, if my size is reasonably large, doesn't affect the topology, doesn't affect the collapse state. All of them will go to the same size of the globular state. The topology effect actually comes into picture only for the smaller size in this particular case. Okay. Okay. Now this is something which was again, I found pretty interesting. One can actually see once you are in the collapse state, in the globular state, what kind of globular states are there. Okay. In the chromatin, people talk about these globules that are there in the chromatin. Okay. Now one can actually quantify how that globule has formed by calculating something called probability of contact between two monomers which are separated by a distance s. Right? How the probability, so if I have a polymer which is going to go to a collapse state, how it has gone to a collapse state, the signature of that is present in this quantity PS. How PS, which is the probability of contact between the two monomers which are sitting at a distance s, very far apart, okay, how does that scale with s, okay, tells you how the globules are formed. For example, if I have a chain with self-avoiding walk, okay, where the collapse state has not formed much, okay, Na equal to 7, okay, let me also tell you what Na is. Na is the number of active sites. So if I take a ring of size 100, let's say, some of them will be active, right? So depending on the number of active sites that you have on the system, you can see 7 also goes to some sort of globule, 14 also goes to a globular state, 21, 28 also goes to a globular state, right? Not only the size of the globule depends on the number of active sites, how PS changes, how PS scales with S also changes with the number of active sites, right? And that goes as 0.5 for, let's say, the red one, which is n equal to 14, which is like this kind of structure, and -1, which goes as for green, which is 21, which is this kind of structure. And in the literature, we have, after seeing this, we actually searched the literature and we figured out that this is the signature, this scaling actually is the signature of how the globules have formed. For example, for the Gaussian chain, where the PS goes as s to the power -5, the mechanism of globule formation is random, monomers coming randomly. So this is a random packing, which is there. Okay, which is actually you can also calculate by calculating the RE, the distribution of RE and putting RE equal to 0, which goes as n to the power -5, which is basically a random movement of the monomer, and finally trying to go to a collapse state. Okay, whereas fractal globule, what happens in the fractal globule, which is seen in biology a lot of time, is along the chain, you will have the globules, multiple globules which are formed locally, right? And all these globules then diffuse or move and forms a bigger globule. Okay, and there the scaling of probability of contact goes as s to the power -1. And it was very interesting to show that depending on the number of active sites you have, right, these kind of different types of scaling is something that you can show here, right? And that was also very encouraging to us, because now we think that this is a model where now I can think of modeling different systems by tuning the number of active sites here, right? Because let's say if I want to model a chromatin of a particular organism, okay, I know what is the probability of contact that is there in the literature. The experiments have shown that, right? So if I want to get into that kind of probability of contact, what should be my model? Move forward, right? Okay. Now this is about the chemo repulsion and chemo attraction. I'll skip that and I'll go to finally the case where about the chain dynamics here also, like the linear case, significant lowering of tau half, which is the collapse time, which is seen by activity. That means activity helps in the collapse of the polymer. The scaling of relaxation time, it has this kind of Zim scaling that we also shown for the linear polymer. Okay. This is maybe the last part that I will try to go into the detail. So far, what I told you in the model of MPC, MD, this chemomechanically active polymer, what we showed is you have a local force which is coming locally on each of this dimer, right, due to the reaction happening. And this reaction also produces this long range forces, and that brings the two dimers sitting very far from each other in contact with each other. Okay, so there's a global force. But in the previous model, in that MD-MPC model, whatever I have talked about, there is no way I can switch off one of them and work with only others. Correct? Because if the moment the origin of both these forces, whether it is local or long range, is the chemical reaction only. And if I switch off chemical reaction, both of them will go away. Correct? So there is no way in that particular case I can switch off one and get the effect of only other, because I want to know which one of these two is actually contributing in the globule formation. Right? So it's not clear to me so far. Now to make that point very clear, Sandeep, who is sitting here, has done this work. What he did is he now has, we forgot about MD-MPCD. He said, let's make it more simpler. Okay, let's take a Langevin dynamic simulation for this model. Here we can put in these FR and FT, and FT is something which is the local tangential force that we have, right? And FR is something which is a long range diffusophoretic force that we had between the two monomer. The origin of that was a chemical field, right? So he said that why not we put them separately, okay, and we can switch off this FR or FT, make one of them 0, okay, and see the effect of the other. Correct? That's a very reasonable way forward, because now the FR also, this long range forcing that we have, is actually a diffusorophoretic force only, which is coming from the simulations that we had with the chemical field, right? So what's the result? Or what did we find out? Now this is first, before going to single one. In this particular model, what do we see if I have a combination of both of them? Okay, so this black curve is the passive polymer, 0.6 scaling, exactly the one what we saw before, right? And if I have a smaller activity, let's see this cyan color, right? Both PT and PR is small. PT represents the tangential local force. PR represents the long range force, radial force, the chemical force, right? In this case, you can see that it behaves like passive, okay, for some time, and then it reduces. The Rg, what we are plotting is Rg versus N, right? But when we have very large activity, which is not possible to achieve in the previous simulations, at very large activity, we see a non-monotonic behavior here. What do we observe? We observe a swelling for small n, and we observe a collapse for large n. Okay, both of them are present. Let's now concentrate only on the orange curve. Okay, the cyan color curve is something like the curve that we showed in the previous case, having the explicit chemical activity, but there was a limitation on how much PT and PR, the forces that we can go to. Now here we can go to larger forces. So what you see in the orange color, that you have a swelling at small n and you have a collapse at large n. This is a non-monotonic behavior that we see as a function of n. Now the question that we asked is, which of these two forces that we are talking about here governs this non-monotonic behavior in the system? Okay, is the question clear? Right? Okay. Now here what we have is what is happening if I have only one of them present. Okay, so you see here we have only the tangential force, here we have only the long range force. What is the long range force doing? It is systematically changing Rg. The long range force also gives you the same scaling, the collapse state, okay, for large n. For short range forces also gives the same scaling, that means the collapse state, okay. However, the long range force on one hand, Rg decreases systematically for all n's, which is not the case for the short range force, the tangential force. So it's a non-monotonic behavior that is coming because of the swelling and all that we see in the small n limit is actually coming from the PT, the tangential force, looks like, right? Okay, so for all PE greater than 0, a higher Rg for small n and lesser Rg for large n with respect to passive, that is what is seen for the tangential force, okay? And for pure Re, for pure radial case, Rg increases monotonically, okay? And it has this kind of a collapse state. So tangential activity, the local activity in this case is something that governs the non-monotonic behavior of the Rg, whereas radial activity always tends to collapse in a structured fashion. Okay, so it looks that at small n, it is the tangential activity that governs. What about the large n? Because large n, both of them are showing the collapse state. For large n, which activity is governing is still not clear to us, right? Now to find that out, we calculated this percentage deviation of the combined, which is this orange color, with the pure, which is this blue and red color. Okay, so the percentage deviation of RG for each of these cases. So what does it mean? It means for whichever case the percentage deviation is less, dominates at that end. Okay, again, I will emphasize this again. So this is my combined, orange one is my combined RG with the combined forces. The red one is the RG when I have only tangential present, and the blue one is the RG when I have only the radial, the long range forces present. Okay, and I subtract this from this from this, and find out the percentage deviation. Okay, now what this inset here plots the percentage deviation. What do you see? At small n, red is smaller than blue. At large n, again red is smaller than blue. The intermediate n, it's the blue which is smaller than red. Smaller means domination of that force. Okay, so what it tells me? It tells me that in this collapsed state at large n, that is what our interest was, right? In the collapsed state, which is the force that dominates, right? And it turns out that at the collapsed state also, for large n, it is the local force that dominates. Very unintuitive. Intuitively, what will we say? That long range forces are bringing everything together. So even for large n, I should have the long range forces which should be responsible for the collapse. Right? That is what intuitively it looks like. But it turns out that even for large n, it is the local forces which is dominating over the large force, long range forces, and the reason, and those are the major reason for collapse. Collapse will happen even with the long range force also, just with the long range forces. But the domination of tangential force, the local forces, are there for the large n also. Right? It's not very intuitively clear why a short range local forces will dominate for the collapse at the for the large length scale. Right? Is my question clear to all of you? Is it clear that in the globular state for a large n, it's a globular state, what we see is, what we see is the local forces that is bringing the collapse state. Okay, long range is also helping, but it's the local which is it is dominating here at this, which is the deciding factor. Okay. Now the question is why? That is what I will try to answer and maybe try to wrap up. Okay, so here this is the root mean square internal distance that again shows a collapse state and an open state. Again, the same thing, whatever we have seen before, right? Okay. Now this is the answer to that question of how a short range local forces is dominating in the collapse state for the large n, okay, for a large distance. Now, what do you see here? This is the bond correlation between the two vectors, between the two bonds, which are sitting at a distance s apart. Okay, so s equal to 1 would means the nearest neighbor bond correlation, then you change the n, and then it's like a persistence length calculation. Okay, now what do you see here? For small n, all of them have similar behavior, very similar behavior, have different persistence length. The collapse dynamics is slightly different. But what is interesting is at large n. That is what our interest was. For large n, if I look at passive case or the case of, let's say, PR, which is these dashed line. PR, remember, was the long range forces. For dashed line as well as for the passive case, what you see a smooth decrease in BS, an exponential smooth decrease in BS. However, the moment you have the local forces coming, you see an anti-correlation in beta S. What is beta S? Is the correlation of the bond vectors. Anti-correlation in the bond vector would mean what? I have this correlation, anti-correlation. It's a hairpin sort of structures. Okay, and that is what we see in case of a tangential force. So what is local tangential forces are doing? They are dominating at large distance. How they are dominating at large distance? Because they are making these multiple local structure, local folding hairpin-like structures, okay, which is helping the overall polymer to go to a collapse state. Okay, so for pure PT in anticorrelated region with maximum anticorrelation at S equal to this demonstrate the presence of local backfolding or local hairpin-like structure that leads to the collapse at large n. Okay, so that way we are able to actually find out which force dominates at what n and why does it dominates at those n's. For small n, domination of tangential force is very is okay because your ring size is small, so this the long range forces will not be able to take it closer to a certain distance because of the topology. Okay, and at large n, again it's that local forces which is dominating. Okay, and that was something which was very interesting, we felt. Okay, and then we went ahead and talked about the relaxation dynamics, how the relaxation dynamics changes with PT and PR. We could see that the slower relaxation for small n could be the local rigidity, large n multiple backfolding results in the faster collapse of the ring for the larger rings. Okay. Okay, any questions so far? If not, I will take this thing. I hope what I made it very clear to all of you. Two different types of models that we worked on. Okay, starting from MD-MPCD, we showed a collapse dynamics of an active polymer, whether it is ring or linear, right? And then for the ring polymer, we showed this kind of collapse state for the larger ends. Okay, for smaller ends, it is not going to that collapse state. Then we wanted to see what is the effect which brings in this collapse state, which we will not be able to quantify in the MD-MPC simulation techniques because we will not be able to separate them. Therefore, we went to a different model where we could now separate them, okay, and then get the effect of each of them separately and find out which is going to be more dominating at what regime. One thing which is something which I have not told you is that in these two models, so far we have not matched the numbers. For example, the dimensionless numbers, activity numbers, right? Peclet. When I say Peclet 20 in this, the second model, and Peclet 20 in the second model, or the activity number, they may not be same. Okay, so we cannot take those numbers very closely. I mean, in those two models, we cannot correlate those two numbers in this model, these two models. But what we can actually tell very confidently, the behavior, the qualitative behavior that we are going to observe in these two models are going to be same. The next task that we are doing in the lab right now is actually trying to correlate these activities very, very, very closely, so that if I say Peclet 10 in MP-MPCD, the same Peclet 10 will be there in the second model. Okay, that's a task, ongoing task that we are doing in the lab. Okay, but qualitatively it is going to remain the same. The quantitative matching is something that is in the process right now. Okay, so now the question is, what if we make them semi-flexible and attach a cargo in front of that, right? That's something, yeah.
I had a question about the correlations. You got an anti-correlation. Is that by calculating fluctuations from a mean?
No, so the anti-correlation here was just by the bond vector correlation, right? So you don't have to subtract any mean or anything here. What you have is these unit vectors, right? And then you correlate these unit vectors.
So when they point in different directions, you get a
yes. Okay. Okay. So maybe now I'll go a bit quickly just to tell you what happens if I make it semi-flexible, attach a cargo. Then what we showed is you can now carry these things, can carry the cargo, And depending on the size of the cargo, depending on the flexibility, depending on where you attach the cargo, the efficiency of carrying the cargo will change. And now we showed that what is the most efficient configuration in which you can actually attach the cargo and move the cargo from one place to other. Okay, this was the quantification of that. Here is the effect of crucial effect of hydrodynamics, which I have just to show you, right? So this is a polymer. If this is the kind of flows that you are going to have, and with the hydrodynamic flow, you see the motion of the trajectory of the polymer. The moment you switch off the hydrodynamics, you see the activity, even if you have the chemical activity. Okay, I'm coming back. I'm doing a switch right now. I have come back to the MDMPCD again, okay? So, so this is where I have the flows. I can switch off the hydrodynamics, and you can see that without hydrodynamics, the motion really slows down. So hydrodynamics is really helping in the motion, right? Quickly, because my time is out. Actually, if you take this, clamp it on one end, you can actually show, because of this this semi-flexible nature, and because of the fluid present and the forcing that you have in the system, it shows a beautiful cilia-like beating. And you can actually now play with the active force and the rigidity of the polymer, and you can make a complete phase diagram where it shows a periodic, when it will show a periodic beating and when it will not show a periodic beating. One can also see a synchronization. Somebody was asking in the morning, right? So if I take two of them and clamp them close to each other, a very nice synchronized oscillation is something that is observed. And we can show, we have shown that the synchronization of the oscillation will depend on the distance between the two guys, because this synchronization actually happens because of the flow between them. If they are very distant from each other, the distance between them is very large, the effect of flows decays, and then the correlation, the synchronization that we see at small length scale actually decays. Okay, so with that, I come to the conclusion. So what I showed you, of course, apart from how we do simulations in the last part, what we actually showed you is the movement of the collapse, the transition of coil to globule and chemically active rings, linear polymer, and then we took it to the semi-flexible part, and we showed the spontaneous oscillations, synchronization, cargo techniques, etc. These are the people who have worked hard towards whatever I have talked so far, and these are the papers from which I have taken the last part of the talk. So thank you very much. Patience.
Previous slide in the cilia motion. So as you said that this synchronization depends on the distance between two polymers. So does it also depends on the length of these polymers?
It will.
So how it will?
Okay, that quantification we have not done, but it will depend on the how the length and this thing is related.
Both will depend. Okay, thank you.
Ma'am, here like the passive particle, they don't form a globule.
In this case, the passive polymer will not form the globule.
But in the
previous one, because here in this particular model, we don't have the van der Waals attraction between the monomers. Okay. We do have this excluded volume, but we wanted to see just the effect in the globule formation. What is the effect of activity? So the passive itself was a polymer which will not go to the globule state. And the model before that, this Vishik model which I was talking, in that case, they had taken the globule, the potential such that you will have the globule formation even for the passive. Okay.
In the Vishik model, there is a polar particles as well as active particles. Both are present, right? And there are some chains which are connecting them, right?
In the in the Vishik model of the polymer.
Yeah,
okay.
linear. Yes.
No, so they all the monomers are to start with, just like the Vishik model. All of them had some velocity, and then they try to get the velocity of their neighbors. Even in this case, all of them are active. All the monomers are active. They all will have some velocity to begin with, and then they will try to get the velocities of their neighbors.
Okay, so they are following the polar particle?
They are. They have
All
them.
active particles
All
are
are active
following the
part-
polar
yes.
particles, right? So here the polar particle is dominating the.
What do you mean by polar? All of them are same active particles.
Yeah, but
Okay.
one is having the directed one,
No,
right?
all of them have the directed motion, but the directed motions are different for different, all of them to start with.
Yes.
Okay.
Yes.
And then they all try to, so now this guy is there, its neighbor is moving that way, the other neighbor is moving that way, the third neighbor is moving that way. So within a cutoff, it will now get the center of mass velocity, and this will try to orient towards the center of mass. That's the Bishek model. Okay. And even here, all of them are, to start with, will have some velocity, and eventually they all will align.
Thank you.
Anyway.
So I just have one question about this, the MD part. So you showed simulations of a ring with chemorepulsion and
Say that again. So, okay, something that is linear and chemorepulsion.
yeah, so without the ring, just linear and chemorepulsion, and what do you see there?
So you're saying that if I have the ring, remove the topology, ring topology, and have chemoattraction and chemorepulsion.
Yes.
Yeah. That's a work under progress. We are doing that. But what I can tell you initially, what we see is the globule state that's very intuitive also, right? The globule state that we observe for the chemoattraction case is not observed for the even for the linear case. Okay, it goes to a stretch state, but depending on the activity and the size of the polymer. Okay, so these are flexible polymer, right? They are all moving. So in chemorepulsion case, what will we intuitively assume that they will try to go away from each other, but the local forcings are still there. So it will have a snaking-like motion. Okay. Now, if the ring size is large and activity is something intermediate, while doing this snaking motion, they actually goes into a caged-like structure. Okay, from which it is not able to come out. Okay, so that part is very, very interesting. And we are doing that right now and trying to get the entire spectrum in our hand. So we see a open state as well as closed state, even for the linear one.
And maybe one more like technical thing. So what is exactly the difference between semi-flexible and the previous model?
The flexible?
Yeah.
So till the last, maybe leaving aside the last few four, 5 slides, everything that I talked about was for the flexible polymer. Okay, before this, everything was flexible polymer. Here, that means what? That means you don't have a bending rigidity. There's no cost of bending for the polymer, right? But with the moment you introduce semi-flexibility, okay, that is by putting some potential, 3-body potential, okay, you are bringing in some cost of bending. So if the semi-flexibility, if the your kappa, which is the parameter and the potential, is very large, it is going to go to a stretch state all the time. Any bending from a stretch state will cost energy and it will not try to go towards it. Does that answer your question?
If you have a flagellum where one end is fixed, and this is a completely flexible polymer, and if you increase the activity, will it form?
Yeah, so that work is actually done by Gomper's group, where they had this helical structure, okay, flagellar structure, and they had multiple of them. Okay, they rotated all of them in the same direction, and that could bundle up, okay, and showed the bacteria propulsion. And the moment they could also show the unbundling of the flagella and this tumbling of the. That's what your question is, right? One single flagella.
Does it form a globular structure?
Oh, acha, okay. No, so we don't have any helical structures right now here. If you really want to talk about flagella, I have to get into the helical structure.
One active linear polymer.
Active linear
fully
polymer.
Flexible, and one end fixed.
So if it is a flexible one, it will go to a collapse state. But if it is Semi-flexible one will not go to a collapse state. It will always show this kind of oscillation. The flexible one, again, depending on the activity, may or may not go into the collapse state. Okay, this is something that I have not really thought about yet. I can discuss that.
Maybe you said that the Peclet number are different. You can't compare the Peclet number at one point. So why is that so?
Okay, so how do we define Peclet number in these cases? This is some quantity that is a ratio of the translational velocity and the rotational diffusion, right? So in the MD-MPCD case, we'll get some Vz, some translational velocity, and some diffusion coefficient. Now the Langevin case, okay, here we are putting some Fs, some forces, some numbers, okay, where I'll get a V and a D, right? Actually, to do a quantitative matching between these two, I should have V and D in both these cases such that the ratio is same. Okay, that we have not done yet. Right now, in the MD-MPCD, I have certain V and certain D that will give me a Peclet, and here my V and D is something different. Okay, so my Peclet here 10 here doesn't mean the same Peclet 10. Okay, I have to do more analysis, more tuning in the model to do a quantitative analysis. But we are doing that. You understand the problem, right?
Sort of. Maybe we can discuss.
Okay, we'll discuss